It's my pleasure to introduce Abel Klein from UC Irvine, speaking on localization in the random x-axis interval.
It's a pleasure to be back in Brazil. As most of you probably know, I am Brazilian, and I am from Rio de Janeiro, and I grew up there. And I used to come often, but with the pandemic, etc. things. I think I've been in São Paulo. When was that meeting? Is that 10, 15? I was in Rio in 2016, but not here. Okay, I used to come very often here at a certain point, mostly Instituto Física, but I would come here, and I have here some old friends, collaborators, and okay, everything I'm going to talk is work with Alex Elgort, who is at Virginia Tech. I am aware that, well, I noticed yesterday, the subject is quite different from what was discussed yesterday. There will be no sister algebras, for one thing. So I'll try to explain what the model, what the problem is, what the results are, and some consequences, and hopefully there will be enough time to give some ideas of the proof. But it's probably better to try to explain things if you're not in the area than to try to prove things and give the details that nobody follows. At least I cannot follow it if it's done to me. So, okay. So everything I'll talk to is work with Albert. Okay, I'm going to be talking about a quantum spin model. The model, and here this is formally, because this is not a Hilbert space, the Hamiltonian is given like that. It has to explain. This is H0. Sigma x, sigma y, sigma z as a Pauli matrices, and I think this everybody in algebra is more familiar with than I am. Sigma plus and minus are defined as usual, and sigma I sharp denotes the matrix sigma, this 2 by 2 matrix acting on the I copy of C2 and acting as the identity everywhere else in the tensor plot. That's a standard thing you always do. And H0. Oh, God, no, I went too fast. Something happened. Okay, I'm sorry. I pressed the wrong buttons. So here you can see the model to explain. H0 is given here. These are the Pauli matrices. So this is H0 is stated in terms of the Pauli matrix is a nearest neighbor interaction. So these are the Pauli matrix. The matrix N is just 0, 0, 0, 1 is 1/2. These are 2 by 2 matrices. And I, of course, means the same thing acting on the ith coordinate. And this explains, this is the field here, the external field. Delta bigger than 1 is simply a parameter. Delta bigger than 1 is the Ising phase of the XZ chain. Delta equals 1, two delta equals 4 gives you the Heisenberg model. Lambda is a parameter. This right now will be just a positive parameter. Lambda doesn't have to be, but I'll just. And for what I want to do, I want to note that H0, this is all at now form. It's not going to be formal from the next slide. It can be by rearranging the terms. you can write as a sum of nearest neighbor interaction plus n of c, where n of c is a total field, if you prefer, total external field, and hi plus 1 is defined, well, minus ni plus 1. Remember, these are these 2 by 2 matrices in the I component, or I don't know how to call fiber in the tensor product, minus this other term, which also nearest neighbor. This is convenient because it does, when I do the finite volume, it automatically gives the correct boundary conditions, which other people impose by hand. So it's natural to do it that way. So now, be rigorous. To be a finite subset, I'll take a finite subset. For here, it can be anything. Later, I'll probably take it to be an interval. H lambda is a Hilbert space. By the way, you can define that Hamiltonian in the infinite volume. You have to define the appropriate Hilbert space. I'm not going to use it, so I'm not going to discuss it. But that's well known, it's not. Yeah, it's well known. And that's a problem usually in quantum spin system. The dimensions grow very fast. They grow exponentially. That means one big difference from Bernoulli operators, where the volumes go polynomially. And the spin chain now given by the Hamiltonian, it looks the same, but I only take nearest neighbors parts that are both contained in lambda, and of course it only makes sense to do that. And of course, these are just take this sum, but for the way we are going to think about it and work with it, the Hamiltonian, the free Hamiltonian can be, by playing with what they are in rearranging terms, can be written as this is a different delta than this. It's unfortunate, but that was a notation that we got from, I think, physics papers and somehow. And where this operator is just given here in terms of, we think of it as a Laplacian, as I'm going to discuss. And these other, what is left after I take those here, is actually what you see is a total number operator, which I will discuss in the next slide, minus the sum of ni plus 1, only in lambda. And this actually plays here a very important role, because if I want to discuss, let me take the canonical basis for C2, 1, 0, 0, 1, up and down, and n takes the up vector to 0 and preserves the lower vector. We interpret the down spin down as a particle, and notice that it's just 2 by 2 matrix applying to Z. Sigma minus takes the up spin to the down spin, takes the down spin to 0, the other one does the reverse. And the canonical orthonormal basis for that, as usual, if I fix A in lambda, I put particles in A, and no particles, if you want to call it holes, you can, and holes outside A. And this, of course, is an orthonormal basis. And if A is an empty set, so you have, I don't know what that is. It's not from this. Never saw that before. And this is the vacuum state, to have no particles. So this is just notation. Unfortunately, I have to go through it. And the remarks is that for intuition, this operator can be viewed as an analog of the Laplacian operator. It is not, it's a very different space, but it has some similar property. Ni is diagonalized by the canonical basis. Ni of phi of A is phi of A if there is a particle at I, and 0 otherwise, if I is in A. So it follows that the total number operator is just diagonalized. You just have the number, for me this is the number of points in A times phi of A. And that's what's really different, and that's what makes this model in some ways treatable. But anyway, it gives it its character. It's diagonalized by the canonical basis. This is always an integer, can be at most a number of particles. This is the number of clusters of A in lambda, so it's the number of connected components or intervals of A in lambda. Consider subgraph of C. So what this tells you, you apply to phi of A is a subset of lambda. So it consists of this number of these, not disjoint, but separate intervals, right? Not connected. This number is W of A. And that's play a very important role. So of course it can be 0, that's for the vacuum, and it cannot be bigger than the number of parts. If A consists of disjoint points, it can be the number of points in A, but it cannot be bigger than that. But that plays a very important role. Oh yes, and the V is also diagonalized because the NI's are diagonalized, but if you do, you find that the eigenvalue here is just the sum of the WI. So everything except the Laplacian-like operator is diagonalized by this base. And you can write what the Laplacian does on that if you want. Not going to do that. And important, we can see these operators N lambda, W lambda, and V lambda commute. And that is not true for most P models, it's true for these, and there's a big thing that makes this model amenable. The Hamiltonian commutes with, not with Ni, but with any lambda, with a total, because the other piece is just this piece, because the rest commutes by this. It commutes with the total number of particles, so it's reduced by the number of particles operator. It plays a role. I'm not going to emphasize and go because there are ways of treating this which don't work for what you want to do here, that basically just restrict to the n particle spaces, where this operator actually looks like a many particle Schrödinger-like. It's a bit different, but very much like a Schrödinger operator, but not here. I'm not going to do that, but still, this plays a big role. Okay, some properties. This is sort of trivial. I look at C4. These are 4x4 matrices, right? Tensor products of 2x2 matrix. And you can do these calculations, and you can show this is a plus or minus or plus, depending on I put a minus a plus because it's no negative. Just calculate the eigenvalues if you want. It's a 4x4 matrix, you can do that. Okay, these imply that this operator, if you look what has, by taking the sum of these things, plus this is non-negative, so, which looks what you are familiar from Schrödinger operator as this is d from the dimension, but it's a bit different. This is an operator, takes different values, but so we have this inequality between operators. And from this, it follows that this operator that is bigger than this, because I added a positive operator, is bigger than this one, using just this simple inequality. So from here, we conclude that the spectrum of this operator in a finite volume, and remember, this is just an homogeneous model, there's no random nothing. This spectrum consists of 0, and then it starts at 1 over 1 minus delta. I'm not giving more details here. And it changes when you change lambda. If you take the infinite volume and make it random, you can prove where the spectrum is almost everywhere, but which It's just actually this, but I'm not going to go there. Okay? So I know that I have 0, I have a gap, and it starts at 1 over 1 minus delta. Delta is less than 1, so this is a positive number. And that's why I need delta bigger than 1 to start with, okay? And delta equals infinity, by the way, it's the Ising model, if you take the limit. And I think delta equals 1, although it was looking, because I think I write it in a different form. Delta equals 1 is supposed to be it's a Heisenberg model, which we cannot treat. We need to have this gap, this positive number, okay? All right. Yeah. Which one? This? No, this is spectrum of, I'm sorry. No, this is a spectrum of this operator. It is standard notation. I didn't even think about it because it's so, I mean, by the way, please ask questions. If nobody asks questions, it's a very boring lecture. So please ask questions, otherwise until nobody's paying attention, right? Better to ask questions. You don't have to ask questions afterwards. Ask questions during the talk. Okay. Which one? Delta equals 2. No, delta equals 2. Did I write it? The coefficient's wrong. The Heisenberg model should be delta equals 1. If it's not, I made a mistake in one of the coefficients. Delta equals 1 is a Heisenberg model. This is written two ways. One you write with sigma x plus sigma x, and I wrote it with sigma plus, sigma minus plus, sigma minus, and one of them is 1 over 2, the other is 1 over 4, and I may have made a mistake. If I did, yeah, it's a mistake. Oh yeah, it's not a Heisenberg model. It's not a Heisenberg model. Heisenberg model, well, up to here, this is correct, except that this is 0. Yeah, so up to now it works, after that it doesn't. Yeah, it should. The fact that this is not 0 is crucial. This model is studied with all sorts of deltas, but we're just doing the so-called Ising infinity. Delta infinity is simply the Ising model because it's everything commutes, it's classical model. Okay. Now we have this estimate, and this just takes these values, right? So this means that there are these energy thresholds. I put this equals K. Maybe I should put the K here, but I did put it here, and K. For that, it turns out to be natural. There are the reasons to define this energy interval, either from minus infinity or from this. It's a matter, it doesn't really matter most of the time because the vacuum is killed. I go from minus infinity to K plus 1, 1 minus 1 over delta, and this starts from here. The reason I wrote with a hat is because for technical reason we need a cutoff, so it doesn't have to be free-force. 1 minus delta is good enough, but we can't go all the way. As you see, we need to have a little bit of room, so basically really we work in this energy interval. And so the K is coming from the W and plays, the properties change because the number of clusters for the free, if you take delta to infinity, the number of clusters change. The maximum number of clusters change. So this is actually very important. And this is also a definition that's used. It's very important. I define projection P plus minus, but P plus S is the sum of 1 minus Ni. So it means that I'm taking the kernel of the number of particle operators in S. So there are no projector, no particles, and P minus is a converse, is a complementary projection. So P plus S is orthogonal projection onto a state with no particles in the set S, and P prime minus S is a orthogonal projection onto a state with at least one particle in S. And these play the role of the delta function for Schrödinger at the point for Schrödinger operator. And you can either say it follows from the definition or do, but P plus of the empty set is the identity, the other one, of course, is here for consistency. Okay, now let me describe an important property which will be the motivation, maybe a posteriori, for what we do after. And that is quasi-locality for this operator. So let me define the resolvent. And this lemma that's proved with algebras in this form, let me take two sets, A containing B containing lambda. A is non-empty and is connected. So A is an interval. Connected set is an interval. Okay? Then I take Z, which is not in the spectrum, so eta Z, which is a distance to the spectrum, is positive. Then if I take the projection into have at least one state in A, put the resolvent, and I have the projection with no states in B. And you could replace B by the connected component containing A. This decays exponentially with the distance from A to B complement. Delta is a parameter. M of Z is actually log of delta times eta Z. I have to make Z bigger than 0. If not, you have to make some modifications in the proof. That's I'm not going to discuss it. It's not a problem. But and it's more convenient for us to actually look at it in this form, because of that means that here you have 1 over eta Z. And for the reason that, although I'm not going to use it, if I take I in lambda and I define IQ to be all points at most at the distance Q from I, then if I do this here, I get this is exactly Q. So that's a more convenient form, actually. Now, the important thing is that localization, that's what we'll be able to find and prove, extend these quasi-localities to energies in the spectrum of H lambda. Now, notice that this only holds for energies not in the spectrum, and the estimate blows up if eta goes to 0. To get localization, we need randomness. That's the usual thing. And that's where I'm going to go now, and that's exactly the subject of the talk. Now, I will mention that later, but if I'm familiar on the Schrödinger operator, this looks very much like the Combs-Thomas estimate, which is a bit different. And actually, if you use the n particle, dividing in each one of the particles, in each one of them, you can actually use a standard proof and prove a Combs-Thomas estimate and get it's a modified Combs-Thomas estimate, which actually gives a better mass. You put a 1 inside, maybe there is another constant. And we did it in a previous paper, but that's not what we're going to do here. We don't want to use properties of the Schrödinger operator. It's simpler to do it that way. But in this is actually very simple. It needs to prove, but I decided not to add any proof. So I will put one proof, it would be that. It's very simple, actually. It's clever, but simple. And so the point is that we want to extend that to energies E, in some sense, in the spectrum, which is what you do for Schrödinger operators, and we need randomness. And so now I'll make it random. And make it random in the obvious way. If you're familiar what to do with Schrödinger operators, you take this Hamiltonian. It's the same as before, but now I make this a random field. and I take the omega i's, y going to z, to be independent, identically distributed random variable, I'll take the probability distribution mu to be absolutely continuous bounded density. I want it to be positive, so, and I want to go to 0 for 0, and I'll make 1 is a support, and I'll put a bound. Because of the lambda, this 1 is irrelevant, because the lambda, they make with the lambda here, it goes up to lambda actually. But so this is just a normalization. So now I make it a random model by making the external field random, and lambda is going to measure the disorder. But there is one extra parameter that you don't have for Schrödinger operators, that there is delta. So these are actually two parameters. When you write the Anderson model, it only has one parameter. I mean, if I can't just divide by lambda like in the Schrödinger operator, this operator here doesn't have any of this. So it actually has two parameters. Okay? So this is the spin chain, and that's the main result from where, and Enrique may be disappointed because you use the fractional moment math. I was disappointed. I'll mention what you can do with the Mutskeler math. Okay, quasi-locality. I fix a delta 0, I fix a lambda 0, and I fix a x between 0 and 1/3. And now I consider the random x-axis spin chain, but I take the parameter delta to be bigger or equal than delta 0. So these are cut off for the parameters. And I can take anything, the constant will change with them. Okay? Then for all k, 1, 2, k equals 0 is trivial, there's not. I can find constants. They depend in delta 0 and lambda 0. Such that, and this is, I have two parameters, remember, lambda times delta square is big enough, but they couldn't be. I have that expectation, I take, looks like what I had before, but I take a fractional moment, that's why, takes expectation. This is the case exponentially with the distance to the complement as before. We get a volume factor. C of 1 is a 0, but it's not 0, and a constant. This holds for all lambda. The constants do not depend on lambda. That's very important. This holds for all lambda, for all finite energies in this space with cutoff. I could have put just ik because there is nothing with 0. For 0, this is 0, so it's trivial. And AB with A connected. Well, before that. This is basically quasi-locality because you can use, but I can tell you all sorts of things. So they say you have decay for this quantity with eventually with good good probability. So this is quasi-locality inside the spectrum. And in this case, we also get that if you take Borel functions with support in this interval and bounded by 1, so the norm doesn't appear, and this quantity, you don't need the S because this doesn't have singularity, it's not, then I get the same thing. The constant change slightly, that's what the prime means. That you do that for Schrödinger operators in a similar analogy. Just to make the analogy, but that's not what is emphasized with Schrödinger operators. But let me rewrite what you do in that way. Consider Schrödinger operator H lambda, and this is a resolvent. Eta z is before. Quasi-locality is a Thomas estimate, but now you have the matrix elements, right? Which also only holds outside the spectrum, and it also blows up when you approach the spectrum. And then make it random. I take Vx to be independent identical distributed random variable whose probability distribution is absolutely continuous with a bounded density. That's the minimal usual. That's be called Anderson localization in general. Also, localization here also yields quasi-locality inside the spectrum. If S, I think, is 0, 1, maybe I need 1/2 here. I didn't check before writing down. If lambda is sufficiently large, all I have to do is to make lambda sufficiently large, depending on the probability distribution. If I take this to the power S, this decay, no, there is no volume factor. This decay with the distance for all lambda, x, and y, and energies. That is one way of proving localization for random Schrödinger operators, and other consequences can be derived from this estimate. For Schrödinger operator, people usually think this is called Anderson localization. Anderson localization, that's a spectrum of the infinite volume operator is pure point, a purely pure point, and the eigenfunction of the case exponential. This follows from this in that case. That's not the case for the XXZ model. These are quantum spin models. The infinite volumes are much more trickier, etc., etc. However, and we don't get matrix elemental. If I go and use the n and go to the n particle sectors where basically you have a Schrödinger-like operator, if I fix n, I can prove a result like that with decay in the half of distance. This is done by many people, including myself and my student son. That's originally done by Chulaevsky and Surov, and there is Alberto, and myself and my student. But this is only for n fixed. And the number of particles here goes to infinity as a number. That's the big difference. And you cannot do that. So I cannot put delta. I can look at configurations and put phi A, phi. I cannot do that here. You can do that for k equals 1, and I cannot do it for k for when you have many clusters. It becomes very different, much more complicated. But anyway, so the analogy Schrödinger operator it is if you write it in a localization in this form. Okay? All right. Sure.
What's the meaning of the resolvent some limiting sense?
I think here.
No, down
Here?
Yeah.
This is a delta function at x. I'm working on L2. Now, this is probabilistic. With probability 1, an energy is not in the spectrum. However, it doesn't blow up when you approach the spectrum. So if you want to put E plus I 0, that's fine. You don't usually bother, but that's fine. This is a random result. So to get results point-wise, you can use probabilistic estimates to get it. But you prove it in this form, and you're right. I should put E plus I 0. Should prove it, and then you can, but that's what it is. Okay? Now, for the other one, notice that here I have P minus of A and P plus of B. These are very different in the configuration. I'm saying there is a particle. I could make A to be just I. I have a particle at I, and this I take it to be what I had before. Nothing. There is nothing close to I. Then I have decay of this quantity. Having a particle here, and I have a box where there are no particles, a forbidden area, then you have decay. So this is different. It is different, and okay, let me make, so maybe you think it's similar, but it's not. It's similar and different, very different at the same time. It's much harder, actually. Okay, comment. This talk up to now, I'll do something, I'll mention that we haven't written yet, not a paper. This is already written, it's submitted and you can look at the archive. It is in the archive. We finished a few months ago. For k equals 1, we prove localization for k plus 1 different, but you think, with Elgart and Gunther Stoss. These appear already. So it's also proved with ours that it was done first by Boden-Varcel. Somewhat different form. And in a form resembling Schwang operator localization result, they only hold for k plus 1. It can be derived from that. For k plus 1, I can have ni and j, which I can't for k equals 2 and I. When I put I had ni and then I had to forbid things in there. For k equals 1, you can derive the result, ni is a resolvent in j. A particle at I and j in the case with the distance from I to j. But this is not true for k. And these are much closer to what one does for Schwang operators. That's probably why you could do it first. And it was much easier to know it. But that other one becomes much more complicated. We also, at that time, proved dynamical. You have to look what it is in the paper, not to go dynamic exponential clustering, which something that only makes sense for quantum spin systems. And in a different paper, following paper, we proved several dynamical manifestations of localization. I mean, k equals 1 is this energy, including non-spreading, things that you do for quantum speed, non-spread of information, zero velocity, Lieb-Robinson bounds, and general dynamical clustering. This was done just for k equals 1. Now, with Elgart and I, we have proved non-spreading, which I will describe the result, non-spreading of information in this energy window for all k. The other things actually, zero velocity Lieb-Robinson bound is not true actually for k equals 2 and I. But non-spreading of information, which maybe you can think is what you want for localization in this system, I think we have proved it's written. The paper is not written, so maybe it has to be checked better, but I'll describe it. Seems to be right. Okay. So now I'm going to try to describe this result, which sort of justifies what you did if you're thinking in terms of quantum spin system. We don't want to prove pre-point spectrum with a decaying eigenfunction, but that's what you are interested in when you look in the literature in quantum spin system. And it's usually proved in the ground state. And this is not in the ground state, it's the reason for localization. We proved it first, as I said, for k equals 1. And you're actually using a local observable. So now it looks more like maybe yes and not. A local observable X with support in a finite, I would only take support to be interval, is an operator this here in Hj, and we consider operator in H lambda, but J is contained, support has to be contained by X as the identity on spins not in J's. I mean, is X tensor the identity on the remainder? The usual thing. It only acts on what it can. And I always take the support J for observer to be an empty interval, and the supports are not uniquely defined. So I'm not going to give you an operator and look for the support. I'll give you the support and say operator is supported in that interval. That's what I'm interested in. Okay? And given an interval J, let's say AB, it's an interval contained in Z, so it's a discrete interval, and I scale L in N, we set JL to be, I span it by L on both sides. I go L, distance L from the interval. Time evolution is standard. Now, suppose, since we only have localization in the energy interval I less than equals to k, we should only expect a manifestation of localization in this energy interval. The same with Schrödinger operators. You only have localization for energy in a given interval. You don't have anything outside this interval. And we can't prove in the whole thing. To certain, although this is saying discrete model, it's actually closer to continuous under some models, in the sense that you can only prove things in the bottom of the spectrum, although here the properties change when k changes, which doesn't happen in that case. But you can only prove things at the bottom of the spectrum. You cannot prove it bigger than 1 for everything. So, okay. We consider the time evolution in this energy. Now, I restrict the operator. I didn't have the P here, and I think I need it, so I have to check. Doesn't matter. And I take this operator and I restrict it to, I cut it outside. I just put energies inside. So this is just the characteristic function of this interval, the spectral projection of H lambda in this interval I less than equals to K. And I define this time evolution, which I'm restricting to those energies. We also then consider this sub-Hilbert space. And that's basically what I have here, call xk. I restrict the observable to that space. And if I write it like that, yeah, because it's the same operator. It's H lambda. P is a spectral projection of H lambda. So they come, yeah. So that's what I'm writing here, just that they commute. That's all I'm saying here, which I have to actually check. I think I need to put the P here, but anyway, that's what I really want. And it's correct. As they commute, so I can put outside, I can put it inside, it doesn't make much difference. And if I put the P's around the E to the ITH, it becomes this one, because the spectral functional calculus. And the paper is not written, but the proof is written, and it's checked, and I think it's correct. But fix k, 1, 2, 0 is not interesting. Assume that the localization theorem holds for this k. That means delta in lambda such that the localization holds this energy. We prove the theorem. And I'm taking the parameters for which the theorem is proven, okay? Now let x be an observable support in an interval J containing lambda. Take lambda to be an interval. And consider L. Well, I want the number of points to be bigger than the size of the support and KL. Otherwise, there is nothing really to look at. Things have to fit. Then, for every T, I can find an observable. It's a random I should have put the omega here. It depends on K, depends on T into it, and it's supported in the interval expanded by L. Such that if you take the expectation I have here, I was just putting K here, I don't know why I have a less than X, that's a misprint. If I have my time evolution and I subtract this is random. This operator is random because this is a random, H is a random operator, so this is a random time evolution. So this is random too. And this means that I'm restricting to the range of the projection, which is random too. And I take this expectation, this decays with L. So we get a volume factor, and unfortunately we get these, and we don't seem to be able to get rid of that. Of course, Lieb-Robinson has a T also, so things are only good for short things, so it's unusual in those models. But This means that for a small time, the propagated operator has support JL up to a small correction if L is large enough. If L is large enough. So it didn't propagate very much. It's localization. For k equals 1, we proved that before, and there is no this factor, and this is not there either. K equals 1 is much easier for everything. K equals 1 means basically have one class. Everything, all the action is on one cluster. K equals 2, we have to consider really two clusters. K equals 3, 3 clusters. Yeah. It means that I fixed a delta 0, I fixed a lambda 0, I took them bigger, and then I got that constant and that, I think it was lambda delta square is bigger and equal than that constant. So the conclusion, so it's more what I really want to say, the conclusions of the theorem are true for this particular choice of lambda and delta. Eh? Lambda 0 and delta 0 I fixed at first. But I can take anything. I mean, the constants I'm going to get are going to depend on my initial choice of lambda 0. So that, I think I call it decay or whatever, lambda dot. So that maybe grow if delta 0 and lambda 0 are smaller. But I still true. So I can take, you can try to, but that, anyway, but for this result is what? And this is much more. But what we're using here is a final result from the theorem. But so this is localization. Information, at least for small time, is not propagating very fast. It's not point back to the exponential decay, but you can get that something is usually proven for, let's say, ground state of quantum spin systems for certain spin. I think Hastings has a result of this kind and something. So this is something, okay. And this is, that's all I'm going to talk about this. Okay, but in the remaining time, I want to just, I'm not going to go through the proof, give you a few ideas that go into the proof. Just ingredients, not going to do the proof. I mean, it's not have time. And if I just went straight into the proof, nobody, I mean, you have to give background, it can't go. That's the theorem which I already stated. That's, okay, that's the main theorem. Okay, so I want to say, what do we do to prove this? And that's what, if I have this, I can prove that last thing that I just mentioned. And as I said, Bishas, this depends on my initial choice here and my initial choice there. So if you want, you can probably write a diagram of. But of course, if delta, if I fix lambda, take delta large enough, or if I fix delta and take lambda large enough, it works. High disorder or delta very, very, very close to 1. I mean, delta going to infinity works, but you don't need it. Somehow, there is some interaction between the two of them. And just, okay. Now, I'll describe some key ingredients. The first one is the quasi-locality that I already described before. That comes into it. How do I use it? Because I can't use for R of E with E close to the spectrum. Well, this is a projection into configurations with M clusters, exactly M clusters. This is a projection between I have 1 to K clusters. Don't pay much attention to that. This thing here is so something looks nice in some formula, but it's not quite important. Okay, so this is the projection of this one, forget, into, I have at most K cluster, okay? W can take at most the value K. W is really that what makes this model different. It's a very important. And now, I define new operators. This one is an important one. H lambda, I add this. K times 1 over 1 minus delta, so this is always bigger than 1, important, times projection with at most K clusters. And I define the resolvent, which of course is only defined outside the spectrum. Good. I lifted the spectrum. I added a positive operator, and it turns out that this operator has no spectrum in this interval. This goes up to K plus 1, 1 minus delta. This operator has no spectrum here. I lifted it. Just an easy estimate, just go write everything. It follows that if I take the interval with a cutoff, and you can see why I need a cutoff, this distance is always bigger than or equals to this. Right? So it turns out, maybe I didn't state the lemma, but the quasi-locality lemma holds for this operator. All these energies are outside the spectrum with a uniform bound. I have this deterministic estimate. Of course, this is not for the resolvent I want. It's for this very modified resolvent. But the morale is that if I replace the resolvent by these other resolvent, we get deterministic K without doing anything. This plays a very important role in the proof. And I'll see later how do we introduce this operator, resolvent identity. When you have a resolvent, the resolvent identity is going to be used at many points. That's why resolvents are so good. Okay, good. The other thing, and there is the same as Schwager operator, actually continuous Schwager operators, not the one used for discrete, is the one for fractional moment for continuous Schwager operators. The theorem is proved by the fractional moment. The first step is to understand that the special estimate is actually finite. Forget the K. If it's not finite, I'm not going to get the K. This is the concept following priori bound. This is a Hilbert-Schmidt norm of the operator. And this is a functional analysis result. It's proved by Eisman, Elgart, Nabokov, Schenker, and Stowe in 2006. And this following, let me take IJ. I'm writing it in the form we want here, but this is a bit more general. They stated for Schrödinger, it's the same thing, Schrödinger operators. Let I and j be in lambda, and I can allow I to be equal to j. Important. That's important. It's actually easier. And let T1, T2 be a pair of Hilbert-Schmidt operators on H lambda that do not depend on the random variables omega I and omega j. And then take S is 0, 1. Then look at this quantity, T1 and I project, I have a particle at I, the resolvent, and J, have a particle J, and T2. I take the Hilbert-Schmidt norm and take to the power S. And T1, T2 do not, the randomness is here. And I'm only taking the expectation, the probability distribution of these two random variables. But Ti and T2 are constant operators for that. They may depend on the other random variables, but they don't depend on those two. And this is bound by a constant divided by the disorder to the power minus s, the Hilbert-Schmidt norm of T1 to the power s, and the Hilbert-Schmidt norm of T2 to the power s. Huh? Huh? I'm slightly over time. Okay, so I'm not going to do much. What I would like to show, just something quickly. Consequences, a priori estimate. The a priori estimate tells the quantities like this are finite. This follows from this. But I need this Q here to get Hilbert-Schmidt operators. You get something like that. That introduces the Q's, which are Hilbert-Schmidt, and introduce those, but those have decay. I'm not going to do much. I just want to say, by doing all these tricks, introducing things like that, if I take a quantity like this, I can write something like this. And when I write something like that, what I have here and what I have here do not depend on the random variables associated with the support of this, with this set. So I can do the estimate and get rid of them and get to something else. I know we use some large deviation estimate, which I'm not going to go into details. It just means I use this property of probability, which is well known. Okay? And we introduce, to be able to do and use the quasi-localities, we have to somehow put things in. There is no time. This is the end. The localization is proved by induction on K, actually. K equals 0 is trivial, just deterministic quasi-locality. We assume the result holds for K and prove for K plus 1. And the details are here. Thank you. Depends on delta, yeah. The field, yeah, look.
My question is, is there some kind of physical limit to do that, or do you think that you can have the result of a economic statement, take a small field to the extent that can just drop?
The delta is important here. So, of course, I could fix delta and just make lambda large. And actually, Bode and Varcel for K plus 1 do that. We don't. We get the results that depends on with algorithms. But this is a much better result, because if you look into the model, I should say that the actual scale is given by the W. And the W does not depend on lambda and does not depend on delta. But somehow you can play with both. I mean, if I've been happy if you just proved it for lambda large. That's good. It would be a good result. But the truth is that you expect that somehow there should be some sort of, so these actually capture some. I'm not saying that delta square lambda is a precise quantity that should be large. That's what we prove. For K plus 1, we had something somewhat different. So I think this is better than, but I don't remember now. So it's just that it has an interplay. Look at, no. What? These are quantum spin systems. Quantum spin systems are much more complicated if it's not on the line. Can we do it? We'll try, but most of the results, if you look for single Z, are still proof because for the chain, that's why it's called the chain. Yes, I would like to prove it for higher than, but for electronic, it's much harder. The things will grow much harder. Now that for Enrique, we tried proved also by the multiscale analysis. For k equals 1, I can prove it. For k equals 2, I can prove it. For k equals 3, there is something I haven't figured out. It's different. This came out first. This came out first. It's a matter of that you don't have locality on it. You don't have like, have the box, you go to the boundary. And it's more complicated. It's propagate, I mean, and as I said, I can do it for a fixed number of particles. That's okay. But I cannot do it uniform. Not yet. Not yet. I have to decide if it's worth doing it or not, now that we have done this. But I think it should be possible, and I have ideas, but there is one place where I thought I had it, and I had overlooked something. But anyway, but this you can do.
So maybe we should defer further questions for the coffee. Abel again.
Okay.
going to talk about a subject which is slightly, so to speak, off stream with respect to what we have been discussing so far, but I hope that I will manage to convey some of your interest and ideas into that. What I'm going to do is to provide or to comment with some ideas we have been working on, still work in progress, to provide a common ground, a common mathematical framework to deal simultaneously with classical and quantum information theory, and some of the consequences of all that. So the plan of the talk will be, first I will make a rough review or comment some basic ideas on the formalism that I'm going to try to generalize or to put together, which is the categorical approach or the categorical foundations of statistics and information theory, by the way. And then, in order to advance into this program, I will say a few words about a neat description of quantum mechanical system provided or that is done, that is obtained by using in a systematic way the theory of groupoids, right? And finally, we will try to, complete the picture, and time providing, the time permitting, I will try to go into some, so to speak, more sophisticated applications. So to begin with, the main idea here is that, as I was telling you, there is a common mathematical background that includes both statistics, including statistical physics, of course, and the theory of information. So to speak, the guiding or the main motivation is this, so to speak, was based on, comes from this observation taken from this the monumental work by Chenkov on the statistical decision rules on optimal inference, and is that where I have substituted the statistician by theoretical physicist, or the mathematician, if you wish, or the mathematical physicist, saying that the job of the theoretical physicist is to construct a mathematical model of random phenomena observed, when studying a physical system. The way to do that, since the foundational work by Kolmogorov is to use probability spaces. This means what I would prefer to call a Kolmogorov space. This means a set omega, the sample space, together with a sigma algebra of subsets and a probability measure defined on that. Such that then, provided that you have a random variable that we will identify in the proper time with physical observables, the expected value is just the average over the space with respect to this measure. Of course, this picture is good. However, we will usually work not with a single system, but with families of systems. And then we need to provide a way of understanding how these systems interact. A particular simple way of interaction was described by Claude Shannon in the 40s, last century, and it's what we call, or it provides the basis of the mathematical theory of communication. For that, Shannon introduced the notion of a channel, which is a physical device connecting the two particular systems, and that we are going to identify, and this is the first step I'm going to take with Markov morphisms. It's going to be also the same as statistical inference rules or transition probability amplitudes. So let me elaborate a little bit on that. So the classical, because we are, the initial step provided by Shannon was this extremely simplified situation where we have a bipartite system. So we have two agents, usually called Alice and Bob, A and B, and each of them, they carry their own sample space, their own probability space, and omega A, BA, omega B, and there is going to be a channel that allows to exchange information. Information is physical, so it has to be a physical device. The way to model this physical channel is by what mathematically we may call a Markov morphism, and a Markov morphism is nothing but, I will use this notation to indicate that for a Markov morphism pi, which is not a map from omega A into omega B, it's not a measurable map, something else. What is that? Well, it's a map that in the first argument is a function on omega A, and in the second argument is a function on the sigma algebra of sets on B, in such a way that when you fix the first argument, what you got is a probability measure on the Bob's space, and whenever you fix some measurable set, delta B, what you got is an integrable function on Alice space, whatever Alice is doing, right? So, yeah, of course, yeah. There are many names. So, and classically, this is, I mean, each, so to speak, domain of science using this use a different name, right? In statistics, called inference rule, in the probability kernel, Markov kernel, there are many, many names, right? There is another way of thinking about that, is that it's a value, it's a measure, probability measure value function of omega A. An idea that it was taken, so to speak, to the next level by Alain Kohn in the 70s to construct the non-commutative theory of integration, which was a main step towards some further developments. But maybe I will say something later on. The point is that this is a very nice, neat, clear picture that I would like to, so to speak, to make it quantum, right? In a natural way. And now I'm going to tell you what are the difficulties. So the first thing that I would like to remark from here is that, okay. So you have a Markov morphism. We have immediately two maps. One that is sending or transforming probabilities in the first space into probabilities in the second by simply integrating on the variable omega A. And there is also a map transforming functions, integrable or measurable functions in the second space into the functions on the first one. By the way, because I'm not going to prove theorems this talk, I would like to give an overview. I'm not going to be as precise as it will be necessary about some of the technical conditions for what I'm saying to be actually true. But if you want, please stop me and I will try to fill in the details, right? So, okay, now there is, well, with this notation that I'm using, this nice associativity property, and the important thing is that Markov morphisms, better if I do it from here, can be composed. The composition is well known and is this Markovian composition law, so we integrate over the intermediate variable. Altogether, what we have, well, this composition law is easy to check that it's associative. There are units here. This means morphisms that compose on the right, on the left, doesn't change what you are observing, right? And finally, the theorem, so to speak, is that the class of measurable spaces, Borel spaces, together with morphisms, which are just these Markov morphisms, form a category, right? That I would like to call the Chenkov category, but I mean, traditionally has this name, stock category, right? Stochastic category. All right, so, by the way, deterministic morphisms are given just by measurable maps from the first into the second space, and then the morphism is just the one that assigns to an outcome in the first space and a measurable set in the second, the characteristic function of the image under f of omega 1. So this means that you have, Alice has the delta probability center or supported at some point omega, then the transformation of this, the process that transforms this delta function, measure into something that Bob is going to use to draw information from the sample space is going to be the delta measured at f of omega, right? So it's completely deterministic, right? This is the meaning of that. Okay. What do we do, or what is the standard setting for quantum information theory? Now we are using this, so to speak, algebraic approach where quantum mechanical systems are described by or have associated some C-star algebras. Let me call them A and B. That will be unital C-star algebras, right? And then these algebras, they are supposed to contain or are part of the information we need to describe the observables of the system. Typically, they are not exactly the observables of the system, which are consistent in general on operators which are not bounded, and of course, elements in a C-star algebra are bounded. But okay, you can work with that and make your life thinking about that. It's the standard situation today with quantum information theory is mainly concerned with results in finite dimensions. So in that case, there is no problem. But of course, we will get into the infinite dimensional situation soon. So now, how this picture, so the classical setting was this row here upstairs. Now, what is the situation in the quantum setting for people working in quantum information theory? Well, now they consider that the quantum channel is modeled by what is called a completely positive operator from the algebra A into the C-star algebra B. By this, I mean an operator such that is positive when we tensor the algebra A and the algebra B by an arbitrary finite dimensional algebra of matrices, right? And it maps the unit in the first algebra into the unit into the second, which is a normalization condition. In the particular instances that my algebras A and B are just type 1n factors, I mean finite dimensional C-star algebras, then this terminology is changed by saying that the quantum channel is given by a CPTP, completely positive trace preserving operator, a map between the algebras. And this is the arena where people are, working very, very hard to understand things which are quite complicated. The point is that, or the problem that I'm facing is that there is, by the way, in this situation, if you have a completely positive normalized map from this linear map from this algebra into the second one, doesn't have to be a star and a homomorphism of C-star algebra, just a linear map, right? Doesn't have to be invertible or anything like nothing, just linear and preserving positivity, right? So if you have a state, let me know by S of beta n, the states in the space in the C-star algebra B, normalized positive functional, linear functionals on B, then it maps, the states on B are mapped by, so to speak, pullback in states in A. So channels, quantum channels transform states into states. This is what physically, this is what we would like to get. But the problem that then I'm facing is that there is a wide gap between this classical picture and this quantum one. What is the actual relation, if there is any, between these two pictures? What I'm going to do is to fill up here in between, providing some common notion that will be embracing both the classical and the quantum one, and that will be done, will be mediated by a description of systems provided by or using groupoids. That's the plan I'm going to follow in the next 15 minutes. Yes, please. Well, not really. Because if they are commutative, then they will be, as you are saying, there will be the space of continuous functions over the spectrum of these algebras, which will be a compact topological space. And so what you got is that your classical spaces, they have some additional structure to begin with. They are compact topological spaces, something that in general we don't need or we don't have in actual classical physical systems, where you only have a measure space, right? Hmm? If you use von Neumann algebras, as I'm going to do in what follows, then you're right. Then the abelian von Neumann algebra will be L infinity of a measure space, and then we will be much closer, right? Are they actually equivalent? In that case, yes. Yeah, in that case, yes. But what happens when you have a genuine quantum system, one which is not classical? This means that it is not an abelian von Neumann algebra. What will you do? How do you will see the common pattern behind these two things, right? That's what I'm trying to, so to speak, unravel. So let me say a few words about, I don't know why this is not, okay. Here, well, I don't have to insist to this audience about the deep impact of the foundations of quantum mechanics, and in particular, the work by John von Neumann had in the development of mathematics, right? But I want to stress that the fact that in the early days of quantum mechanics, there was a fundamental notion that in some sense has been, put aside or put under the carpet, which is the notion of transition, of quantum jumps in the terminology of all quantum mechanics. This was the seminal idea by Heisenberg that was actually contained explicitly in the first paper, or one of the very first, the foundational paper of quantum mechanics, where the emphasis was that the physical phenomena were not related directly to the, in those days, there were the stationary orbits of the system, but with jumps or transitions, this is a literal translation, between two different orbits. This is with emission of absorption frequencies. He wrote in that paper a composition law, which is the composition law of a groupoid. This fact has been neglected for many years. Actually, Kohn in 1995 recalled that and saying that this composition law was the law of the groupoid of pairs, and mainly because, it was, so to speak, a sort of banalization, of trivialization of Heisenberg thinking by Jordan, saying that, okay, what this guy is doing is just multiplication of matrices. This was true because of the simple case he was dealing, because the algebra of the groupoid that he was using is just the algebra of matrices. So he was rediscovering the composition of matrices as the convolution product of a groupoid. This is exactly what I'm going to, so to speak, take as a fundamental principle from now on. But again, this fact was rediscovered again by Schwinger, the same Schwinger of the KMS states we were, enjoying yesterday a lot. And it was again neglected after his work. The main idea, the first sentence in his book is that the laws of atomic physics must be expressed in a non-classical mathematical language that constitutes a symbolic expression of the properties of microscopic measurements. And immediately he writes down an algebra, he called it the algebra of selective measurements. I'm not going to enter into that, just to put some context. That is exactly the composition law of a groupoid, again. So, so this is some of the historical background. So let me take, so to speak, seriously back the ideas by Heisenberg, by Schwinger, by Kohn, all of them, and let me tell you how I will describe a quantum mechanical system from first basic, simple physical principles. So let's construct the actions. So we will be describing a system in this room, whatever. Rodrigo, for instance, which is sitting there. Then we will have some experimental setting, and we will be taking measurements of what Rodrigo is doing, where it's located, the mass, the position, the velocity, whatever, right? The energy, whatever physical quantity you want to measure, right? And you will get some outcomes out of that. So let me call the space of outcomes A, B, X, Y, etc., and they will belong to some set. They don't have to be numbers, if you wish. They could be colors, they could be, signals fired by detectors, for instance. I mean, we may be carrying, I could be carrying a Geiger detector, and this detector could be, you know, emitting signals and cracking because of the radiation that I will be getting, right? So outcomes will be elements on some set. And then what we will observe is that together with the space of the outcomes, there are transitions that we are observing. So there is something that was by detector was triggered when I was sitting here, and after a while, the detector was triggered when I was here. So there will be a transition telling that something happened that when I was measuring my position here, and after a while I was measuring my position over here, right? So these transitions, they will form a set, and they will have a source. Sorry, Jan, I'm not going to use the R and D notation you were using yesterday. The range and domain, I'm using source and target. But I couldn't change all my transparencies in such a short notice. So, so the transition, they have a source, which is the value, the outcome of the measurements of the various apparatuses we are using before something physical happens, and the outcomes, which will be the target after some physical phenomena has happened. For instance, you might think in a more, so to speak, traditional standard situation that we are observing an electron in an atom, and then we are reading the energy at a given time, and after a while we are reading the energy again, and there's been a transition from some energy level into another energy level. We detect that because we capture some energy emitted by that, some photon, right? Okay. These transitions can be composed. There is a natural composition law, which is just the concatenation of physical concatenation of them, right? In the laboratory, we are observing things, so we are registering what we got, and then if there is a transition from A to B, and then a transition beta from B to C, then we can compose, and we think that we have a transition from A to C, given by the concatenation of these two transitions, right? This composition law is the composition law. Sorry, in the previous picture, there was a graph, one of the original spectroscopy pictures of the different emissions and transition between energy levels in an atom. So you may think that this composition is just constructing paths in the graph that we are obtaining by primitive measurements, right? Of course, there is the space of composable transitions, and the composition law comes from natural physical concatenation of events, of experiments, of observations, and the axioms that follows from this is that this composition law should be, now we are imposing that, associative. There should be units. These units usually are, in physical terms, neglected, because it means that nothing happens, right? We do not observe anything happening when we measure, when we are observing our system. And the final one, the existence of inverses, is a very interesting one. I'm not going to say a lot about that, but it's saying that if you are observing some transition from A to B, so some electron which is dropping from one energy level into another one, there should be also the transition that allows that this electron will be excited from some energy level into the other one. And well, this is arguable, right? So you may say maybe not. But Feynman was very explicit in his PhD thesis in 1948, was stating as a fundamental principle in nature what he was calling the principle of microscopic reversibility. That meaning that when observing, so to speak, fundamental physical processes, there is no privileged arrow of time. There is no way to distinguish between past and future, right? So this meaning that if you observe some transition in your laboratory, this means with a clock, that clock over there, right? There is no reason that there is that the clock couldn't go the other way around, so we will be observing the inverse transition, right? So if there could be a copy of this laboratory, of this classroom somewhere where the clock is running in the other direction, right? And there will be no way to distinguish between the two possible situations. This is a way of stating this Feynman's principle of microscopic reversibility that implies that if you want to describe in an abstract way what you are observing in your laboratory, you have to use a groupoid. For any transition, the inverse must also be there. If not, we will just keep with categories, which is also good, and it's a way of talking about, this is the way of talking about causality and so on, but I don't want to enter into that. So, some simple examples. So humor me and come with me with this very simple example. For instance, the qubit. The qubit is the simplest possible non-trivial system, which consists of just the groupoid with two elements, two objects, plus and minus, and one transition, and its inverse, together with the units, right? In a schematic way, or in a simplified way, this is the groupoid corresponding to this graph, which is the A2 in terms of linking diagram. This is why I'm calling the qubit the A2 qubit, right? And this is the fundamental, simplest possible quantum mechanical system described by this groupoid. More complicated, the harmonic oscillator. It will correspond to the A infinity group, linking diagram, which is the diagram consisting of an uncountable number of nodes, and is generated by the transition given by from n to n plus 1, and the inverse from n plus 1 to n for any n, natural numbers, right? There are many more, of course. But let me, before giving more examples of that, what I was telling you before, is just purely kinematical and algebraic, right? There is no randomness. And remember, the first transparency, the subject or the job of the theoretician is to provide a model, a mathematical model for random phenomena that we are observing. Of course, we have, for classical systems, this idea by Kolmogorov, the notion of measured spaces. What is the natural extension of this idea if together with the outcomes that we are observing, we also want to incorporate the transitions, right? So how do we extend this notion of this Kolmogorov idea to a groupoid, right? Well, this idea was the subject of a lot of reflection by many different people, starting with Mackie and with many remarkable contributions by Pieter, Alain Kohn, Jean Renaud, which is here with us, and many others. And so to speak, a kind of consensus emerged, more or less, considering that the natural way of extending the notion of Kolmogorov spaces to groupoids is what we call a measure groupoid. So without being technical, a measure groupoid consists on, of course, we have to have a measure on the basis space. This is a diagrammatic representation of a groupoid. So the elements in the plane, in the window, in the screen will be the transitions on the groupoid. There is the set of outcomes of objects, if you want, of the groupoid, what in the notation by Jean Renaud was gamma 0 here. And there are the two maps, the source and the target maps. So if alpha is a transition, the source map is telling us what is the source A, and the target map is telling us what is the target of that transition, the outcome of this transition, which will be B. The preimages of the target map will be denoted by gamma upper A, the source. Oh, sorry, this is, okay, this is wrong. This gamma A should be here, sorry, this one. This is gamma upper A, which is the inverse image of under the target map of A, and gamma B is the inverse image. I mean, all the transitions that end up at B, right? Then composing on the left with alpha, we transform things that end up here on A and things which end up on B. So we have a natural translation, family of translations on a groupoid obtained by multiplication with the groupoid law on the right or on the left. I'm using on the left now, but you can repeat verbatim what I'm saying using on the left. So the natural groupoids do not have hard measures, like in the case of locally compact groups. But there are, or we may select families of you want a measure valued function defined on omega that assigns to any A, to any outcome here, a measure which is supported on the corresponding gamma A on the space of transitions that end up there, and which is equivariant with respect to left or right translations. This is what is expressed here. This is Kahn's terminology. He called a transverse function on a groupoid a function on the space of objects with values on functions supported on the fibers of the target of the source map, or the random or the domain map, and which are equivariant with respect to the natural translation by left or right multiplication. This is what, for instance, by Jan was called a family of hard measures, right? And the point is that if you have a family of hard measures whose existence can be proved under technical conditions, together with a measure, a probability measure on the base, we can integrate them to obtain a measure on the groupoid, which is not canonical in the sense of hard measures, left or right invariant hard measures on groups, which are almost canonical, so in the sense that they extend in a natural way a given probability measure on the space of objects, right? If you read this formula here the other way around, so you are given nu, you can disintegrate this nu under some technical conditions again to obtain this family of measures along the fibers of the source of the target map. And then a measure groupoid will be a groupoid equipped with a Borel structure. Sometimes, I mean, depending what you want, you put some technical condition. For instance, you ask that gamma is a standard Borel space, or even more, it's just an analytic Borel space, for instance. And a class of measures here, these brackets indicate the class of measures containing nu that has to satisfy some property with respect to the inversion. What do I mean by that? Okay, in the groupoid we have the inversion, right? To any alpha, to any transition, we have this map associating the inverse transition. Now, if we apply that map to the measure mu, we will obtain the push forward of the measure mu with respect to the inverse. We will denote it by nu minus 1. And then the Radon-Nikodym, well, we are assuming that the inverse is lying in the same class, it's equivalent to nu, and the Radon-Nikodym derivative of that will be a function delta, which plays a very fundamental role, which is called the modular homomorphism. It's actually a homomorphism of groupoids, and it's together with the transverse function and the transverse measure P characterize the full integration theory of the groupoid. This is a result by Alain Cohn. In what follows, in order to, I mean, these deltas, these modular homomorphisms, they propagate, I mean, they populate almost every formula that we will write in what follows. So I will simply assume that the groupoid is unimodular, so the delta is 1, but keep in mind that in general there will be square roots of delta, and so all around. Okay, so examples of measure groupoids are provided by the examples we have been listening yesterday, various lectures. I mean, action groupoids. So you have a group acting on a set, which is measurable, which is a Borel, carries a Borel structure, and the action preserves that Borel structure. Then, oh, sorry, this should be a comma here. There is a canonical groupoid associated to that, which is just the couple of the groupoid of pairs of elements in the group and the points in omega. The source of the couple Gx is just X, the target is just the translation of X by G, and the composition is given by this simple formula, which is simply acting twice with G and G prime elements. And then this groupoid carries a measure structure coming from the structures. In the case that G is a locally compact group, the hard measure on the system of Haar measures, or the transverse function, will be given by the Haar measure on the group itself, and the measure on the basis space will be given by B, the measure on omega, and this is, so to speak, the main source of examples of situations of measure groupoids, right? There are other, just to finish this part, there are other groupoids which are not this form that I like to call kinematical groupoids, that they are going to play an important role in the foundations of quantum field theories. The idea is that you have a space-time, M, with some metric, Euclidean if you wish, or Lorentzian if you are dealing with relativistic quantum field theories. Then there is the Riemann groupoid, which is the groupoid consisting of isometries from the tangent spaces to the manifold M into the tangent at the point X into the tangent space at the point Y of the manifold M. And, sorry, this linear map is an isometry. It maps the metric at Y into the metric at X, right? This is clearly a groupoid. The composition law is going to be the composition of these linear maps. This is not just a measure groupoid, it's just, is a Lie groupoid. There is a smooth structure here, induced from the smooth structure on M that propagates to the groupoid. This can be extended in the case that M eta is a space-time, in a metric a Lorentzian space-time, what we call the Poincare groupoid, and now the groupoid consists of triples where Px is an element in the cotangent bundle of the manifold, it's a covector, it's a momenta, and Py is another momenta, Txy is as before, it's an isometry that transforms the momenta Py into Px, right? So these are examples. By the way, the particular instance where you have Minkowski space-time, so the flat space-time, dimension 4, with the action of the Poincare group in there, the action groupoid is isomorphic to the Poincare groupoid of the Minkowski space. So these groupoids extend in a natural way the situation where we have a symmetry group, which is the Poincare group that we want to preserve, to situations where there are no symmetries. I mean, if you have your flat space-time and you put a small perturbation there, for instance, me here, then the metric in the space-time is not anymore flat. And generically, there are no isometries of this space-time. So this is a major problem in quantum field theory, how to do relativistic quantum field theories in space-times which are not flat, right? Exactly. Then the point will be to begin starting working with the groupoids, right? And in that case, the first step will be to extend Wigner's program that considers the construction of elementary quantum systems. I mean, for Wigner, the main contribution, or one of the main contributions, was to identify that elementary quantum systems, particles with mass and spin, they were in one-to-one correspondence, so they were described by unitary reducible representations of the Poincare group, something that he characterized in this famous paper, 1939. But now the same idea will be, okay, if you are in a space-time which is not flat, what will be the notion of an elementary quantum system? I mean, the particles, they will be the fundamental excitations of whatever quantum field you have there, where there will be reducible unitary representations of Poincare's groupoid. Now, you have to work out the theory of representations of groupoids, so you have to extend and to think about the basic ideas, means the Mackey's imprimitivity theorem, and when you do that, you discover, for instance, that there is a one-to-one correspondence between irreducible unitary representations of the Poincare groupoid over there and irreducible unitary representations of the Lorentz group, standard one, together with the orbits determined by the condition P mu equals m squared. So there is a nice, simple recovering of basic ideas in this context, very naturally done using groupoids. Okay. Let me say a few things about observables and because I'm going to need that, and I will jump into the algebra of observables of a quantum system is identified with a von Neumann algebra of operators on a Hilbert space. So the algebra of observables of a quantum system is a concrete C-star algebra, right? And not only that, it's one that is closed in the wake of the strong operator topology in the algebra of all bounded operators on the Hilbert space, or because of von Neumann's theorem is equals to its bicolmutant, which are equivalent notions. In an abstract way, you can say that a von Neumann algebra is a C-star algebra that has a pre-dual also too, and you don't need the Hilbert space. But if you want to do physics, something that sometimes is advisable, then you go better than to select a concrete realization of your algebra in terms of operators in some Hilbert space. In this sense, the question is, if you have a quantum system described by a groupoid, where does the algebra of observables come from, emerges? I remember when I was a student in physics, in mathematics you didn't ask these questions, but I was always bugging my teachers, my professors, saying, okay, according to Dirac, if you have a quantum system, you associate a Hilbert space to that quantum system. But how do I know where this Hilbert space comes from? I must say that I never got a satisfactory answer to this question. I mean, how do you guess, how do you know, how do you understand what is the Hilbert space that you should associate to your physical system? To me, for instance, I'm a physical system. So what is the Hilbert space which is associated to me, right? Well, you start mumbling something and then you say, oh, your particles, and so you take the tensor product, and the truth is that nobody knows. Well, maybe yes, in the sense that we can start for a more fundamental situation. So just the kinematical description of quantum systems that I was telling you before, provided by a groupoid. Is there a natural way to construct a von Neumann algebra? A von Neumann algebra, which implies that there is also a Hilbert space there associated to this groupoid, and the answer is yes, there is a natural way of doing that. Could be a little bit involved if we consider the general situation where we deal with a measured groupoid, but in the case, for instance, that gamma is a countable, discrete, unimodular groupoid, the construction is very easy. All you have to do is to consider the left regular representation of the groupoid, which is given by that. This C of gamma is the algebra, the algebraic algebra, finite linear combinations of elements on gamma into the space of bounded operators on L2 of gamma. So this is the space of square integrable functions of gamma. Notice that gamma is a measured groupoid, so there is a measure nu there, right? And lambda of alpha on a function psi is just psi translated on the left by alpha minus 1. This, of course, provided that alpha minus 1 and beta are composable. It means that the target of alpha and the target of beta are the same. If not, this should be 0 if alpha minus 1 and beta are not composable, right? So this is the left regular representation. There is also the right regular representation. And then you just simply define the von Neumann algebra of your groupoid as the double colmutant of the image of lambda and the lambda of this finite algebra, right? Or the closure in the weak operator topology, which is the same. You may extend this construction by using, in the case of topological groupoids, the convolution algebra. You pick up the family now, if gamma is a topological groupoid, now locally compact, you select the family of compactly supported functions on gamma and you define the convolution using the standard formulas, and then you make functions act as operators on the space of square integrable functions on your groupoid by convolution. There should be a square root of delta of the modular homomorphism if the groupoid were not unimodular, but it's okay like that. And then again, you construct a closure of the image of that. Again, this is the natural von Neumann algebra associated to your groupoid. So this means that there is a natural, I mean, if you start with this more fundamental approach, this Heisenberg idea of transitions, there is a natural von Neumann algebra, and then this question about where the Hilbert space comes from is irrelevant. The Hilbert space will come from states on this von Neumann algebra via the GNS representation. Right? So provided that any state of your system that you consider will give you a Hilbert space, it will be the GNS Hilbert space associated to that state. Okay, so just to finish completing the family of examples, so I have a few minutes before my time is over. So, some simple examples. In the case of finite groupoids, this means that the space of the von Neumann algebras of these finite groupoids are going to be finite von Neumann algebra. This means direct sums of algebra of matrices. So direct sums of finite factors of type 1. So the particular case of the qubit, the von Neumann algebra is the algebra of matrices 2 by 2. In the case of the harmonic oscillator, what you got is the algebra of bounded operators on L2, which is the factor of type 1 infinity. In the case of action groupoids, the von Neumann algebra of the action groupoid is just the cross product algebra, corresponding to the action of G on the abelian von Neumann algebra of essentially bounded functions on omega. In this sense, we can define the type of a quantum system as the type of the von Neumann algebra associated to that, to the groupoid describing the quantum system. Of course, we have states and the GNS representation. I'm not going to insist on that. The important thing is that, because of what I'm going to say later, is that, for instance, in the simplified setting where we have a countable discrete groupoid, if you have a state, the algebraic version of the algebra of the groupoid, it means finite linear combination, they sit inside the von Neumann algebra. So the state being a map from the von Neumann algebra into the complex numbers can be restricted to the groupoid itself, defining a function on the groupoid. This function associated to the state satisfies a positivity property. So this phi here is just the restriction of rho to gamma, and it's a positive definite function. This means, in the sense of Gelfand, Naimark, and so, satisfying this positivity condition, the positivity condition which is inherited from the positivity of the state, right? This is just substituting things. Together with a normalization condition provided by that. Because von Neumann algebras are unital, and this unit in the von Neumann algebra is going to be the formal sum of all the units in the groupoid, right? That's what it is. So, states, at least in the case of countable discrete groupoids, are in one-to-one correspondence with positive definite functions. Actually, there is a reconstruction theorem by Naimark that can be extended to the case of groupoid, that if you are given a positive definite function, you can reconstruct everything from there. In the case of measured groupoids, which are not countable discrete, well, the thing is a little bit more complicated. You have to put some conditions on the general representation of the state, and provided that the representation is non-degenerate, you can prove that there is this positive definite character of the representation associated to that. I was going to say a few things about classical systems and the quasi-classical approximation, but I think I'm going to skip that and to move into sorry, but I mean a couple of words about dynamics. Just to connect with many discussions that we had yesterday. Many of you were focusing on dynamics, on some one-parameter group of automorphisms, right, which are going to be the dynamics, the actual dynamics of a quantum mechanical system. The point is that and a lot of the questions were concentrated on the construction, on the description of KMS states for a given dynamics. And here I'm going to take the other way around, right? Assuming that, I mean, von Neumann algebras are dynamical. What do I mean by that? That associated to any state, there is a flow, there is a natural dynamics. And the way to construct it is via Tomita-Takesaki theory. I'm not going to insist very much on that. That automatically provides a modular flow, associated to a state which is good enough, which is separating and faithful. I'm going to enter into that. So there is, starting from some state that could be, that can have some particular physical meaning, and natural dynamics associated to that. By the way, the state rho is a KMS state for the modular flow corresponding to that state, right? That's automatic. This seems a little bit involved way of constructing the dynamics of a quantum mechanical system, and there is a question here that I just want to point out, is that there is an alternative to that, and the answer is yes, and this was the idea that Julian Schwinger was pursuing all his life. He came up with a notion that was a quantum variational principle. He had in mind that in classical mechanics, we obtain the dynamics as the Euler-Lagrange equations of some Lagrangian, some classical action, right? And one of the ideas that he had in his mind was how to provide, how to obtain the dynamical description of quantum systems, even more of quantum field theories, by using a variational principle that has to be quantum in a way. And all these things that he was, these Groupoids things and all these things were focused trying to do that. He did that, and he was using that, but in a very, very formal way. So no rigorous statements, no mathematics, let me say in a different way. They were very deep mathematics, but without a real understanding of that. Very much like when we were using Dirac's delta functions without, prior to the theory of distributions, right? Very much that. So this is something we have been working a lot, trying to develop that, but this is not the time, neither the occasion to talk about that. So let me just use my last 5 minutes to tell you how do we manage to put these two pictures, the classical, Markovian setting with the quantum information, with these completely positive operators and all that. Of course, the first thing is to move or to transform the picture of the positive operators into something which is more, close to the notion of a Markov kernel. So let me call a quantum Markov. So we have now two von Neumann algebras. So now the algebras of observables associated to the physical system we are describing are going to be von Neumann algebras, M1 and M2. Then a quantum Markov kernel will be a map from the dual, the topological dual of M1, M1 prime times M2, satisfying a few properties. The first one is normalization property. This means that if we evaluate with the unit on the second algebra, we get 1, no matter which, the thing we plug here in the first argument is positive in the sense that for any row in the first argument, what we got is a linear map on the second one, which is positive, right? And these two together means that what we got is for any row, this pi is going to determine a state in M2. So actually, in this definition, it will be sufficient to put here, instead of M1 prime, the space of states on M1. But just for mathematical purposes, we are using that. Finally, there is a property, well, there are two more properties, reflexivity, that are needed to define in a proper way the composition. And means that if we fix the second argument, so an element in the second von Neumann algebra, in the first one, this is going to be an element in the bidual of M1, so in M1 prime prime, right? M1 is contained in the bidual, but they don't have to be the same. So the condition is that when we fix the second argument, the linear functional that we got on M1 prime has to be an element on M1 actually. And finally, an hermiticity property that reads like that. with these conditions, which are, if you wish, a little bit technical, we can define the composition of two quantum morphisms, quantum Markov kernels, in this way. You have P12 from M1 into M2, Pi23 from M2 into M3. So they have to be a map from M1 prime times M3 into the complex number. So rho 1 is an element in the dual of M1, and A3 is an element in M3 here. So how do we define this number? Well, this is going to be Pi1 evaluated on rho 1, and the second argument is the element on A2 provided when we fix, because of reflexivity, when we fix A3 here. It is going to be an element, in this case, in M2. This is why we need reflexivity. Then with this composition law, what we got is that this composition law is associative. There are units that are defined very simply. I mean, you have the unit from the von Neumann algebra M into itself is going to take values on the dual and the elements in the algebra. It's just the valuation on rho and A. And this allows us to define a category that we call the NCP category. NCP, because it's the acronym of non-commutative probability spaces, NCP. Also, because NCP is also nonlinear completely positive, well, sorry, normal completely positive states, and also because this is the, well, there are various games playing with words that are not good. So this category has the states are going to be, the objects, sorry, are going to be pairs, von Neumann algebras and states. So rho is a state in the von Neumann algebra, and the morphisms are going to be quantum kernels that transform the state rho 1 into the state rho 2. This is work in progress with Florio Cialia and Laura González Bravo. Actually, is the content of Laura's thesis. The analysis of this category. Of course, this category is too large. And we usually work with subcategories of that, what I like to call quantum environments. A quantum environment is a subcategory that, for instance, is finite. Because, of course, these categories are so large that for practical purposes, they are useless, right? Not for conceptual or for theoretical purposes, but for practical purposes, they are useless. Now, and this is the last, I have 2 minutes, good. Of course, groupoids provide von Neumann algebra, so we can restrict this previous definition when we are considering von Neumann algebras coming from groupoids, right? And in that case, we have a, so to speak, an abridged definition of category, what we call the groupoid NCP category, which are given by kernels. Let me call them groupoid Markov kernels. What are they? Well, they are very simple. And this is very good news because they allow us to work, I mean, working with operators and with algebras, you know how hard it is. But working with functions on concrete sets is much easier, right? So what we are doing is to transform problems. We are passing problems from the abstract domain of algebras and operators into problems about functions on products of groupoids. So if you have two groupoids, gamma 1 and gamma 2, describing the quantum system associated to Alice and Bob, our two people which are interacting and communicating, then a quantum channel for them will be a map from the Cartesian product of both groupoids into the complex number, satisfying, well, the natural conditions inherited from the previous transparency. Some normalization condition here, and some positivity condition. That means when we fix the first argument, in the second one, this has to be a positive definite function on the groupoid, the second groupoid. Some Hermiticity condition, here's the delta, the unimodular, sorry, the modular homomorphism. The composition law now is exactly the same as the one we had for classical Markov morphisms, integrating on the intermediate variable, right, here. And of course, now proving that this is a category is much simpler. The objects are going to be groupoids and states determined by this characteristic, positive, definite, normalized. Well, if you want to remove normalization, then we will work with weights, but it's also good, no problem. And So the objects will be quantum systems given by the groupoids associated to them or determining them, and states given by normalized positive definite functions, and morphisms will be these quantum kernels, and they will fill up this line in between, providing the natural, so to speak, way of considering, by the way, a particular class of groupoids are totally disconnected with trivial isotropy groups. This means sets, right? And then the von Neumann algebra of a set groupoid is just the algebra of L infinity functions on that set. So in this sense, your initial question is exactly now completely natural and clear and transparent here. When the groupoids are classical, then we are here. And when the groupoids that describe non-classical systems, we got this, well, the completely positive, the completely conditioned, I have skipped it. I mean, I'm not going, I have not incorporated into this definition here because probably it's not so fundamental. But okay, so this is the framework. This was supposed to be, okay, the end of the talk so far. Now I have a, a sign indicating various roads we could take, but of course just for you to know that we have been working on symmetry theory, generalization of Kramer-Rao statistics and the Fisher-Rao metric, causality, Bell inequalities. I could say a few things about any of this subject, but I will leave that for private discussions or for your curiosity if you are interested on that, and I will stop here because my time is due. So thank you very much. Yes, please. Okay, this takes, I'm not going to abuse your patience. The main thing, yeah, that's true. So of course I cannot, explain that without abusing the time and the patience. But the point is that the Bell inequalities, sometimes, some people call it the most, the Bell inequalities and the violation of them, somebody or some people consider that they are the most profound result in science, not in mathematics, not in physics, in science of all time. This is arguable, of course, right? Depends. But it's a very fundamental thing. Actually, the Nobel Prize in Physics this year was given to Aspect, Clauser, and Zeilinger, just exactly because the experiments they performed proving that the classical Bell inequality was violated in concrete experiments. Bell inequalities is a consequence of classical statistical probability theory, and essentially states that if you have two classical systems and you have two pairs of observables, well, the Bell inequalities, I like to to describe them as the consequence of three principles, which are, so to speak, unobjectable, which are realism, freedom, and independence. That sounds very much like a political slogan, right? But this is what it is. Realism means that world at the end is described by a classical probability system, the Kolmogorov setting that I was writing in my first transparency. Independence, that I and Rodrigo and we are far enough, we can operate as independent of each other. So the observations I will get here will be completely unrelated with the observations that Rodrigo is doing over there. And freedom, that I can do whatever measurement in my laboratory that I want, and Rodrigo can do the same, no restrictions, right? You are free to do whatever you want to do in your laboratory and I in mine. With these three principles, then you prove with some little, well, actually the proof, once you set the formalism, is that if Rodrigo and I are measuring observables that take the values minus 1 and 1, A for Rodrigo and B for me, and then we measure the expected value of this combination of, this is the tensorial product, but the product of this function, right? Because these observables are just functions with values, functions on omega 1 and omega 2 with values in 1 minus 1, and we take the expected value with respect to whatever classical state. This means probability density on the Cartesian product of omega 1 and omega 2. This will be always smaller or equal than 2. The proof is one line, because here, if you take common factor A1 in the first and A2 in the second, you have B1 plus B2, B1 minus B2, and because they take values in 1 minus 1, if one is 0, the other will be 2, and vice versa. And you integrate the average over, you bound that by 2, and then you integrate over your probability, and you get 2. So this is the proof of what is called the CHSH Bell inequality. So under these three assumptions I was telling you before, realism, independence, and freedom, you always, this inequality has to be satisfied. This is the Bell, well, it's a refinement. This is not the original Bell inequality. This is why it's called with these names here. But this is the fundamental inequality. And the fundamental experiment is that this inequality is violated in actual experiments. Right? That's the fact. Right? Actually, when you measure these quantities for 2 photons or 2 electrons that are correlated, what you get is that this quantity is exactly 2 times the square root of 2, which is strictly higher than 2. Right? This is, so some of the first, so if this is violated, it means that the actual working of the world, of the universe we live in, one of the 3 axioms has to be false. Either there is no realism, there is no classical description of the physical systems that we want to understand, or independence, or you have to renounce to independence or to freedom. Of course, there is a law, there is a vast literature on that. I mean, we can be restricted by some powers to do only some experiments, you or me, independently that you are living, let me say it the other way around, that I'm living in Andromeda and you are living here in Sao Paulo, in Brazil, right? But of course, this is unreasonable. So the only way to get to understand what is going on is to replace realism by some sort of weak realism, right? There is no classical variables model behind the theory, right? Impossible, because then we will have this inequality, and this inequality is violated, right? So, however, so this is the situation, right? You were asking about that. When we use a groupoidal description of quantum systems, you can restate realism, because now observables are going to be functions on the groupoid, self-adjoint functions with respect to the von Neumann algebra structure. On the von Neumann, you see the von Neumann algebra of the groupoid is generated by functions on the groupoid. It's a closure of the space of functions. The functions act by convolution, right? It's a non-commutative algebra, but it's generated by actual functions on the groupoid. So there is realism, right? These functions are defined there. So what is implicit in what I was saying before that is not correct? Well, it makes that, with that, sorry, I promise that I will stop in a moment. Okay, so here we have to bar this part, no existence of a Kolmogorov model for the physical universe, but the groupoidal one, if you are happy with that, is a good notion of realism. In that case, the only inequality you are able to get is this one, which is an application, I mean, I'm going to explain of what is called the Grothendieck's inequality. So in fact, a slight generalization, and tells you that this is the only, in that situation, bound that you get. for the measurement of products of that. And then when you use this, there is no contradiction because there is no the smaller or equal than 2. Actually, when you apply this picture, right, we're now using instead of classical Kolmogorov model, the qubit groupoids, the A2 I was telling you before, then you got exactly that when you plug here A1, B1 plus A1, B2, the CHH inequality, you got that this is going to be a smaller or equal than 2 square root of 2, which is what we observe, right? So we restore, so to speak, a sort of realism, but now based on groupoids, right, instead of classical Kolmogorovian models. Okay, just to give you. I mean, okay, I'm sure that there are a lot of questions that you may ask if you, I mean, you were not shy to say, okay, I don't want to bug you with fundamental questions about the meaning of things, but I hope that in the after, I mean, out of this formal thing, you will be, I will be happy to hear your comments or questions or, you know, criticisms that are sometimes more important. Okay.
So I guess since we are a little bit over time, maybe we should bring Alberto again to this very next talk.
Okay. Thank you.
thank you very much. It's truly a pity not to be there. I know that everybody is having a fabulous time over there, and I'm here. But I'll try to participate remotely at the best of my capabilities. So the talk that I'm gonna give you today is probably on, well, a bit different topics than the ones that are treated in the rest of these conferences. But I still hope that it might be of some interest because random matrix models are truly everywhere. So what I want to tell you about is, well, some models that actually emerge also in statistical mechanics, which are called random matrix models. And I want to study them and look at their phase transition, basically, using the tools that come from integrable systems and integrable PDEs. And my plan is basically to try and define in a suitable way a thermodynamic limit for this type of models and use PDEs to try and understand what happens in the thermodynamic limit. But as of this slide, this is just a bunch of buzzwords which don't mean much. So let me just, bring everybody up to speed to what I mean with these, words. So maybe some of you are already knowledgeable on the topic of random matrix models, but as I was mentioning, they are really everywhere in mathematics and physics. And one of the things that you discover when you start getting into these topics is that actually they link together so many different fields, from QFT to number theory, to, again, of course, statistical mechanics, and so on. What do we usually mean by random matrix model is basically looking at probability distribution over suitable spaces of square matrices. Usually, the space of square matrices we have in mind might be Hermitian or symplectic or symmetric, so have some, feature that define them. And usually what we have is that the probability distribution has a form that is really reminiscent of what you have in your standard statistical mechanical models. So you have basically a Gibbs weight of the exponential of minus something, and that something is the trace of a potential, and that potential typically takes the form of a polynomial. So you could think of this dm as a linear combination of powers of m, and you're just taking the trace, and that's a really standard form for this sort of models. And of course, a probability distribution to be such needs to be normalized. And so here you have these partition functions that appears that is just, the normalization constant that makes sure that the probability distribution is indeed well defined and normalized. So some of the standard models that people look at have as potential just m squared. So basically what you have is the matrix equivalent of a Gaussian. Okay, so I'm sure that many of you have heard about them. And so these models, when you're looking at Hermitian matrices, take the name of Gaussian unitary ensembles. And when you're looking at symmetric matrices, they take the name of Gaussian orthogonal ensembles. So these are basically just, again, the equivalent of a Gaussian distribution on either Hermitian or symmetric matrices. What I'd like to look at is sort of deformations of the GUE and the GOE. So what happens is instead of having just a square weight, we have truly a polynomial with also higher degrees. Okay, and if that's the case, then our partition function takes the form that you can see here, where here dm is the standard R measure over the group, and the group might be the one of the Hermitian matrices or the one of symmetric matrices, depending on what you're interested about. And when we look at Hermitian matrices, then this model takes the name of HME, Hermitian matrix ensemble, symmetric matrices, symmetric matrix ensemble, SME. So I'm going to refer to HME and SME throughout the talk. So this is just how the partition function looks like. And what I'd really like to understand is what happens if I change those parameters pk that I had in the partition function before. So let me just go back a second. If you see here, I have a polynomial here, the exponential, which again plays the role of my potential. And here, okay, I have the Gaussian, but here I have that is deformed with these powers, and each power comes with a coupling constant, which is called Ti. So you would have T1 trace of m, T2 trace of m squared, T3 trace of m cubed, and so on and so forth. And truly, these T's are the equivalent of coupling constants in statistical mechanical models. And the goal of this investigation is to try and understand how the model behaves when we tune these coupling constants, okay, when we tune these parameters. The way that we're going to try and do that is to explain the fact that there is a well-known correspondence, a well-known relationship between matrix models, matrix ensembles, and integrable hierarchies. So the hand-waving idea is that this partition function corresponds to certain solution of certain integrable differential equations. So that's the main tool that we're going to exploit. And of course, we'll need to suitably define what we mean by thermodynamic limit here. So of course, naively, what we mean is that the size of the matrix goes to infinity, but how we actually take that limit is actually a sticky point that we're going to take a look at later on. And as everybody here, I'm quite interested in phase transition. And of course, here I'm going to be maybe a bit more hand-wavy. When I say that phase transition, by phase transition, I mean sudden change in the phenomenology of the system. By that, I mean that there are going to be the equivalent of order parameters in standard statistical mechanics, and a change in their behavior is going to be what signals the appearance of a phase transition. And for the sake of this talk and in this work, we focus on the case where our potential only has even powers, so you don't have odd powers here in your partition function. So it means that your deformation of the Gaussian is just as weights like T4m to the 4, T6m to the 6, and so on and so forth. So as it is now, I mean, it looks pretty compact, but it's not straightforward how we can actually do calculations on this partition function. But thankfully, this partition function can be rewritten in a much more, explicit way, and this is a very well-known result by Weil. So far, everything I've said is just review of better people than me. And so the point is that the traces, if you think about it for a second, just depend on the eigenvalues. And here the potential depends just on the traces. So the idea here is that when you write the R measure, you can actually split it in the eigenvalues and everything else. And you can integrate away everything else, and you just get an integral over the space of eigenvalues. But that would just be Rn. So we managed to actually rewrite this partition function in terms of just an integral over the eigenvalues. And that's what I've written here. So Z is actually proportional to an integral over just the eigenvalues. C is just basically what we get from all the degrees of freedom that we integrated away. And tau is just this integral here. So what you see is this product just mimics exactly the way that you had here for the traces. So you have the exponential of whatever polynomial you have. But what you get from this change of notation, because at the end of the day is almost akin to a change of notation, you get a bit extra, which is this delta, which is called van der Monde determinant, which is just an ordered product of all the differences between different eigenvalues. And depending if you're looking at the SME or HME, the van der Monde determinant here appears with a power 1 or a power 2, so it's 1 for the SME and 2 for the HME. And it seems like this might be a trivial difference, but it really isn't. And we're going to see that the behavior of the HME and SME are actually quite different. So long story short, this tau that I've written down is basically the same as the partition function. All the behavior of our model is encoded in the tau exactly in the same way that is encoded in the partition function. Again, this tau, of course, depends on the coupling constant T. So throughout the talk, I'm actually going to be looking at this tau. And maybe sometimes I'm going to refer to it as tau function. Maybe sometimes I'm going to refer to it as partition function. But my take-home message here is that this tau is the object we want to study because it's essentially just like the partition function of the system. Is just a smart way of rewriting it when you're dealing with matrices. Okay. I know that this is probably something that you already know, but the reason why we're interested in the partition function is that if we take, for example, logarithmic derivatives with respect to the coupling constants of the partition function, what we get is indeed the moment of your distribution. So it means that, in a sense, the partition function or the tau function encodes the behavior of the system. So everything that we want to know should be somewhere in there, in a sense. Okay. So for the rest of the talk, the tau function is going to be one of the main objects that we're going to take a look at. Okay. So now that I hope I've brought everyone up to speed on the background, my idea would be to take a look at some recent-ish results on the HME that I had in collaboration with Antonio Moro from Northumbria University, and then see what happens in the case of the SME. And again, that's work in collaboration with Antonio Moro and Marco Dell'Atti. On the idea that the HME is, well, you're going to see in a second that in the case of the HME, we managed to look at phase transition, and we do find something quite, peculiar. But we have to do a bit of work to get there, so just bear with me. So, again, here I will need you to do a leap of faith, because I'm not going to do all the calculation, but I hope you can trust me when I say the things that I'm saying. So let me here define Bn as, well, you could think, so Bn is just this combination of tau functions here. So you have this ratio of tau n plus 1, tau n minus 1 over tau n squared, where tau n is the tau function of the remission matrix model, and n is the size of the matrix. So here basically the ratio of partition functions at size n plus 1, n minus 1, and n. Okay? And there is the square root. Because of course they're within the Gibbs weights that's hidden in the partition function. So this B is going to depend on the coupling constant as well. So we could think of it as a function of a discrete index n, which is the size of the matrix, and a continuous set of parameters t, which are coupling constants. And basically what I'm going to do is that I'm going to build this matrix, which is called the Lax operator, which is just this symmetric three-diagonal matrix where I'm going to just put B1, B2, B3, B4, B5, etc., 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 on the upper diagonal and lower diagonal. And this, of course, is a semi-infinite matrix because n can take whatever value because it's just the size of our matrices. Okay? And the point is that it has been proved it has been shown by Adler and Van Merbecky that basically we know how B evolved in terms of the coupling constant, which if you think about it, it's something huge because B is basically a combination of tau and P are coupling constants. So we know how this combination of taus evolves in terms of the coupling constant. So, and this is all encoded in this commutator here. So you have that if you take the partial derivative of L with respect to any of your coupling constants, T to K, this is going to be given by this commutator. So here, skew is the skew symmetric part of L to K. If you're interested in how exactly that looks like, please ask. But this is just something slightly technical. And here L is the matrix. So you're just taking this commutator, and you know how the B evolved in terms of that specific coupling constant. The point is that this equation here, which is called the Lax equation, is sort of already very well known in the integrable system community, because this is just what is called the Lax equation of the Toda hierarchy. This set of PDEs that you get from here is called Toda hierarchy. Well, actually, it would be the Toda hierarchy if we were taking every coupling constant. So we were considering of having both odd and even degrees in our polynomial, in our potential. But here we're just taking the even one. So it's actually a restriction of the Toda hierarchy to even times only. And in the literature, this restricted hierarchy also takes the name of Volterra hierarchy. But the point is that this equation here encodes how the B's evolve in terms of the coupling constants, and the B's you can think of as the B is your order parameter in a sense. So just to give you a flavor of actually how these things look if you write it explicitly, let's just look at what happens in T2, where calculations are reasonably straightforward. We need to calculate that commutator, okay? So L squared takes this form. This just, you can do it with Mathematica, it's an easy computation. You build your L, you take L squared. Its skew symmetric part is this one. And if you take the commutator, that's what you get. And let me remind you that L on the left-hand side was this one. So here, what you have is that basically for T2, for the first for the first coupling constant, what you get by just, equating what you have on the left-hand side here and on the right-hand side here, you get this identity here. So for any n, it's easy to check that that's what you get. Okay, so you have that Bn evolves in terms of P2 in this way here. Okay, that's the first equation of the Volterra hierarchy. And so here what you have is that basically n, which remember is the size of the matrix, sort of plays the role of a discrete space, and T2 plays the role of time. So in general, the coupling constants play sort of the role of time of the hierarchy. That's why we call them T. And that's why sometimes I'm going to call them time and sometimes coupling constants. But the take-home message is that the coupling constants of the model here are the times of this hierarchy of differential equations. Because remember, I have one such equation for each time, for each coupling constant. But of course, as you all know, differential equation has infinitely many solutions. We are looking at that specific solution that can be written in terms of our tau function. Remember, this Bn is defined as a certain square root of a certain ratio of tau. So we're interested in that specific solution. So that specific solution can be identified with the initial conditions, basically. And it is a straightforward calculation to calculate Bn when all the coupling constants are 0, because then the integrals that come within the tau function are all tabulated. They're called Salberg integrals. What you find is this. So we're looking at this specific solution of this hierarchy. Okay? So that's what I was mentioning at the beginning, that the tau function of, in this case, the emission matrix ensemble is linked to a specific solution of the Soda hierarchy. Okay? And so what I'm trying to see is whether we can actually understand what this B does. How does it behave? Because at this point, this B is playing the role of the order parameter. Okay? And so just to make our life simpler here, I'm taking the square of small b and I'm calling it capital B. So again, capital B here is this just ratio of tau function. And the point is that we know how to write that evolution explicitly for any t, for any coupling constant. We know how to write it explicitly. Of course, these expressions get uglier and uglier for the higher degree you're taking a look at, so for the higher coupling constant you're taking a look at. But we know how to write them. So it's a bit of speculation. But if you ask me, okay, how does it evolve in T12? It would take me some time, but we know how to do it. So that's not a big deal. And the point is that based on a result on the whole Soda system, we can see that something similar holds also when you're looking just at the system with even flows, and that's the theorem that we have here from my recent work with Antonio. So the point is that we actually can write in a recursive way the solution of these, hierarchy of integrable hierarchy of PDEs. And that's how it looks like, okay? So these B's here are just the specific combination of the fields B that you add here, okay? So this is just the V's that we had before that, as I told you, we know how to calculate. They're just combinations of products of B's at specific sites, and specific difference in N. So this is actually quite an explicit expression. I mean, it's not extra nice, but still it's an explicit solution. And this is called the string equation, and it generalizes a result by Jurkiewicz from 1991. So what I'd like to do is actually, see how it looks like. To do that, I need to decide which polynomial I'm looking at in my partition function. So of course I cannot keep all possible degrees. So I'm just gonna say that my polynomial is a 6th degree polynomial. So I'm gonna put any coupling constant from T8, T10, T12, etc. They're all gonna be equal to 0. And I'm just gonna imagine that my potential is T2 trace of M squared, T4 trace of M4, and T6 trace of M6. And of course, I will need T6 to be negative, because if you remember how the partition function looks like, I need the higher degree, the coupling constant of the higher degree to be negative. Otherwise, at finite size, my partition function would not converge, which of course wouldn't make much sense. So we have to have a constraint on that. But for the rest of this talk, I'm going to take a look at the case t is equal to 0, t tends equal to 0, and so on and so forth. So keeping up to t6. And what I want to do is to understand what happens in the thermodynamic limit. So as I told you, it's a bit of a sticky point how to define the thermodynamic limit. So the way that we're going to do it is looking at the limit as the size of the matrix going to infinity as the continuum limit of this hierarchy. Because if you remember, the small n here, let me go back, the small n here sort of plays the role, plays the role of a discrete space, okay? So instead of saying n going to infinity, I'm going to say something that's morally equivalent. That is, I'm going to take this discrete space, so you could think of this as a field on a discrete lattice, on a discrete one-dimensional lattice. I'm going to say, okay, instead of looking at a discrete lattice, let's look at what happens on the line. Okay, so I'm going to take a continuum limit in that sense. In order to do that, I will need to do some rescaling to make sure that everything works properly. So I'm going to set a large integer capital N, and I'm going to define epsilon equal to 1 over n. And morally, this epsilon you could think of as the spacing between neighboring sites. And the idea that this epsilon is going to go to 0 as we go towards the continuum. And I've rescaled appropriately all my parameters. So my b's, I've rescaled and I call them u, but that's just nothing, there's nothing deep in this. And again, I've rescaled with respect to epsilon my coupling constant, and this brings forward a natural rescaling for my v's, which remember are just combination of the b's. So these two things for the u's and the v's are consistent one with the other. So what happens if I take the continuum limit? So if I take this that is in discrete and I send it to the continuum, okay? So here I've defined u as basically the continuum limit of my discrete function un. And what happens is that if we keep up to t6, at the leading order, this expression here is nothing but a cubic with the coefficients depending on, well, x, which is basically the continuum variable that supersedes the small n that we had before, and the coupling constant and the times. You see here it's 2, t4, and t6. So this is just a cubic equation. One might ask, yes, we had this expression as a solution of a hierarchy of PDEs. How does that hierarchy of PDE look like? So this thing here should be the solution of a hierarchy in the continuum. And indeed we can do that. And what we find is that if we do it at the leading order, we find that our continuum limit order parameter, fulfills what is called the Hopf hierarchy, which is one of the standard hierarchies that are out there basically. So, but this is at leading order. And remember that here we have correction. We can write corrections at any order actually. We know how to write these with corrections at any order. It's just that if you write it in a compact way, it looks very weird. And I think that the leading order is probably a bit more informative. But so the phenomenology of the HME now in the thermodynamic limit is encoded by this U. And as I was saying, at leading order, U is a solution of the Hopf hierarchy, which is basically this one. Here, CKs are just some number, like we have them written there, like I think the first one is 2, 1K here is equal to 1, but these are just numbers, so nothing fancy. So U is a solution of the Hopf hierarchy, and it satisfies a cubic equation. And that cubic equation, that solution, develops singularities in finite time. If you think about it a second, a cubic can become multi-valued, which doesn't make much sense for a function. So the problem is, how does this system of PDE, how do these PDE resolve this singularity when this pops up, okay? And the point is that we actually have a hint of what happens because, as I told you, we know how to write all the corrections at higher order, and these are dispersive corrections and not viscous ones. And this is going to play a very, very important role, as we're going to see in a second. And the point is that we are going to characterize the phase transition of this model based on the singularities of this system. Just as for any statistical mechanical model, the singularity in the order parameter is what fixes a phase transition, and that's the same here. So the point is, how does this phase transition looks like, given that I have a cubic solution of the Hopf hierarchy with dispersive correction? So here I'm trying to, paint you a picture, or better said, I'm actually trying to show you sort of a movie so what we have here, all these plots are in X on the horizontal axis, and we're plotting U, and I fixed T2 and T4, and I am evolving an epsilon, and I am evolving in T6, okay? So from left to right, top to bottom, you could think of it as a movie where T6 is getting bigger and bigger. So it's getting closer and closer to 0, because if you remember, it was negative. So this is basically a plot of your order parameter. So what happens? Here we have two lines. We have a black line, which is the solution of that recursive equation. And then we have also a dotted line, which is just the cubic. But we know that there's something amiss with that cubic because it's going to become multi-valued. And indeed, that's what happens. So at the beginning of this evolution in T6, we have a smooth cubic solution, and indeed the discrete and the continuum solutions just perfectly overlap. Then here we have the gradient catastrophe. So we have that basically here the cubic develops an infinite slope, an infinite derivative. And we see something starts happening here if you look at the solution of the recurrence relation I showed you before. And here, if you keep going, you have these very specific oscillations that develop, okay? We have some quite striking features, because as you can see, they have very fast oscillations, but their amplitude is sort of modulated. Their amplitude is oscillating as well, but more slowly than the wave itself. So the order parameter has a very specific, undulating behavior. And this sort of behavior is well known in the field of dispersive equations, and it's called a dispersive shock. And as I was telling you, this sort of shock is characterized by having two scales, this fast oscillatory scale that you see here, but also this low modulation scale that tells you how the amplitude of the oscillation changes. And so the point is that usually in statistical mechanical models, this is not the type of shock that you find, but you find what is called classical shock. So from this point of view, the HME is sort of it's presenting a new feature, because that's not something that is usually seen in statistical mechanical models. And so in this sense, in this case, the phenomenology of the model is described by the appearance of these phase transitions that are signaled by this sort of very specific oscillation, this dispersive shock that propagates in the space of coupling constants. Because remember, here I'm showing you basically a sort of a movie where I'm evolving in T6. Okay, so this is just propagating in the space of coupling constants. If there are any questions on this, you can let me know now, and you can let me know later. Of course, here I'm skipping a lot of stuff just to give you a bit of a flavor of what we're trying to do. So this is basically what I wanted to tell you about the HME. So now I'm going to turn to the SME. As I mentioned, this is a result with Marta, Delatti, and Antonio. Marta is at Portsmouth University, Antonio is at Northumbria with me. And so the SME, if you remember, its partition function, its tau function, had this form, and the only thing in which it differed from the HME was that the van der Monde determinant here is just, absolute value, that you don't have that squared that you have. But we're going to see in a second that's going to make a huge difference, and the SME is actually going to be quite more complex than the HME. And you see that straight away. The way I want to go about it is exactly the same. So there are some known results on integrable hierarchies. In this case, there's going to be another lattice. So I'm going to tell you about that lattice, and then we're going to do the thermodynamic limit. So the idea, the structure of my reasoning is exactly the same, but we're going to see straight away that in the SME, everything is quite more complex. First of all, if you remember, for the HME, we had just that one order parameter, that Bn, okay? here I have infinitely many order parameters. So that's already quite more complicated. The easiest one to write is the one that we've labeled with 0, which is very similar to the Bn that we had before. So it's just these ratios of partition functions at different sizes. So again, here 0 is just a label of which order parameter I'm looking at, and plays the role of a discrete space we're going to see in a moment, but it's just the size of the matrix. And here the coupling constants, because the taus here depend on the coupling constants, so the W is going to depend on the coupling constants as well. And we can define actually infinitely many coupling constants, and we are labeling them with K, where K can take value in Z, so K can be negative or positive. This is just for a matter of simplicity of notation. And WKN, we can write down a suitable combination of partition functions, their derivatives. So it's just ratios and products and sums of partition functions and their derivatives. Okay? And so again, here N is just the size of the matrix of the matrices we're looking at. And what we do is that we arrange them. We arrange these order parameters, these fields, in a suitable way in another Lax matrix. This Lax matrix is going to be basically its upper triangular part is going to be all 0, apart from this upper diagonal here, where we put the field W0. You see here, as we go down this diagonal, the size of the matrix here is increasing, and we put in a suitable way the other field within this matrix here. Okay, so as we go down the matrix, what happens is that basically we are increasing the size of the matrix. And again, this is a semi-infinite matrix, and it just gets bigger and bigger. And things sort of mirror what happens for the HME, but again, here things are more complicated. But again, there's a theorem by Adrian van Merbecky that ensures us that we know how the L evolves in terms of the coupling constants. But if you remember, again, here within the L, we have our order parameters. We have some suitable combinations of the taus of our partition functions at different sizes. So basically, this identity here encodes how the model evolves in terms of the coupling constant. This projection here is way more complex than what we had before for the HME. So I'm not going to go into the detail of how that's defined. I have some backup slides on that if anybody's interested, but this is just a technical detail. Basically, you can just project this matrix in an appropriate subspace and take this commutator and find how these W's evolve. And this Lax equation here is Lax equation of what's called Pfaff hierarchy. It is, this hierarchy of differential identities, 142, 144, 146, 148, etc., it's called Pfaff hierarchy. To be precise, the Pfaff hierarchy would be the one with also the odd coupling constant, which we have put to 0. So we're actually looking at a restriction for the Pfaff hierarchy with even times only. So again, also here, small n is going to play the role of a discrete space. So we're looking at fields on a chain. And the coupling constants are going to play the role of time. So I'm not going to do the calculation because it's not as nice looking at the one for the HME. And as you see, the equation for the first flow for the coupling constant T2 already look way more complex than what we had for the HME. So this is how the fields with a negative index evolve, the first two equations. That's how the field with index W0 evolves. And then we have W1 and WK with K more than 1. And so, as I mentioned, again, here, the Ks, these upper indexes, are just indexing different fields. And we have infinitely many of them, and plays the role of a discrete space variable, though originally, remember, it's the size of our matrix. But here, in the context of these differential identities, plays the role of a discrete space variable. So you could think of fields on a chain. And here, T2 is the first of the coupling constants. And just as in the previous case, there are infinitely many solutions to this hierarchy, but we're looking for that specific solution where the W's can be written in that specific way in terms of the taus that has that specific form. So there is a correspondence between the tau function and a specific particular solution of this hierarchy of differential identities. And we can identify it with the initial condition. So the initial condition we can write quite easily for the zeroth field, W0. That's just calculating the taus, the partition functions, putting all the coupling constants to 0, so you basically have just a Gaussian. But now we also know how to write the initial condition for any field, and that's not actually in this work. It's part of our work in progress that I hope to be out reasonably soon. So just to, really, stress this, the SME is way more complex than the HME, even just based on the sheer number of order parameters that you have, okay? Nonetheless, we want to study the thermodynamic limit anyway. And the way we go about it is exactly the same. Instead of looking at n that goes to infinity, if we think of this n as, discrete positions on a chain, we're going to take the limit where actually, instead of a chain, we have a continuous line. That's why it's called the continuum limit. And I'll go about it exactly as before, in the sense that I'm going to define a scale epsilon, which is unwaveringly a measure of how close the sides become. And I'm going to define a continuum variable x and an equivalent set of fields of UK, which is just going to be the continuum version of our discrete field WK. Okay? So while WK depended on n, discrete sides on lattice, UK is going to depend on x, continuous variable on a line. And at the leading order, of course, we have corrections in epsilon, and we know how to write them. But at the leading order, so the lowest order in epsilon, what we have is that this is how they look like, how that bunch of equations that I had before, this one, the continuum limit looks like this, which is not as ugly as it might seem at a first glance, and it's actually a very, very nice model. It's actually a very nice set of PDEs. Why so? Well, the point is that the equations that I've just shown you have a very specific form. So if you look at it for any field UK, its evolution is given by something U0x plus something else U1x plus something else UX of k minus 1 plus something else again UK plus 1x. And all these something else's are just suitable linear combination of products of fields at neighboring sites. Okay? So it has actually a very nice and compact structure in a sense to be an object that encompasses infinitely many fields. To be precise, these sorts of objects have been studied in the literature and are called hydrodynamic chains. And the point is that they can be written, an hydrodynamic chain can be written in this way, where U is just the vector of the field. In our case, it's an infinite vector because U, the K, can take values negative and positive. We have infinitely many fields. A is an infinite matrix, and UX is just the vector of the spatial derivative. So it's just a quasi-linear set of PDEs. And here, so this A here is going to basically contain all these elements, AK0, AK1, etc., etc. So within this A is going to be a sparse matrix, and within this sparse matrix, the elements that are non-zero are going to be a linear combination of products of the fields. Okay? U0 and U1 play a special role, and for this we call them seed of a chain. So before I get to the last couple of slides, maybe some of you are aware of other objects of this type, like the Benny chain. So chains are very well studied objects in integrable systems, and the point is that this is a novel chain that is, at least to the best of our knowledge, hadn't appeared in the literature before. And there has been quite a lot of work on how to define integrability for hydrodynamic chains, which you're going to see straight away it's not obvious at all, given that you have infinitely many fields. And what we managed to prove is that it is as this chain is actually integrable. So this hydrodynamic chain is indeed integrable. I'm not going to go too much into the detail of what integrable means in this context, but just to give you an unwavering idea, it means that fixed any finite n, one can find a well-behaved solution U, such that every field actually can be written just in terms of n dependent parameters. Okay, these are these R1, Rn. And these are called reduction. So solutions of these types are called reduction. And in this sense, we say that the SME hydrodynamic chain is integrable in the sense of hydrodynamic reduction. And our chain is interesting also from another point of view, that is that there has been a classification of integrable hydrodynamic chains. There are criteria given how your chain looks like, how that matrix A looks like, to see whether it's integrable or not. But due to some specific features of our case, basically that we have two seeds, our chain eludes this classification. So we truly found a novel example of integrable hydrodynamic chain that eludes the classification that was by Odesky and Sokolov, I believe, but I don't remember the year. So, and then I guess it's going to be lunchtime for you guys there. Just to wrap this up, basically we've taken a look at the HME and the SME, and the way we went about it was very similar. We exploited the fact that the HME was related to the TODA hierarchy, so hierarchy of integrable PDEs, and the SME was related to another hierarchy that's called the FAF hierarchy. And we took the continuum limit as a proxy, if you wish, for the thermodynamic limit. What we found is that for the HME, we actually have an explicit solution via generalizing equation. And we do manage to look at the phase transition of this model, and we see there is another type of phase transition that's characterized as a dispersive shock. So what I really want to say is that that type of oscillation has been observed for the HME, but were not defined as, were not classified, if you want, as dispersive shock, but we're able to say that those are dispersive shocks because we know how the higher order corrections that we have for the Hopf hierarchy and for our qubits look like. So in this sense, we find a novel type of phase transition. And for the SME, actually, the things are a bit different because we don't have, at least at this stage, an explicit solution, an explicit recursive solution, but we do find a novel structure anyway, which is this hydrodynamic chain, which is indeed integrable in the sense of hydrodynamic reduction. And thank you very much for listening to me, and thanks. And I believe I cannot hear you because I seen you all clapping, which was very nice, but I couldn't hear you. Probably the microphone is off.
Is there any question? Okay, peraí. Okay, peraí. Okay, so is there any question?
So I can see you, but I cannot hear you.
Not here.
And I think that maybe you're muted in the call, I'm not sure.
In the past, are you able to hear us? No, maybe. And now? No? No.
The microphone. It's up.
Here? Are you listening now? No? What do you think? And now? No? Okay, let's just tell her. Wait. This one? And now? No. I don't know, there is in the chat, no? Maybe. Okay, wait, is it full screen? No. Chat. We are not able to fix the sound. So very So let's see. Okay, wait.
That might be difficult, or you might write them in the chat.
No.
Or
No.
you could go to lunch. I think those are all the options.
No. O Fred não tá aí, Aguinaldo. Peraí, 1 minute. 1 minute. E aí, Fred? Eu que vacilei aqui? Tá funcionando, mas ela não ouve nada. Fred, você que salva aí, cara. Não. O Rui mandou tentar todas. Are you listening? No. Tá indo, mas para outro lugar.
I cannot hear you. I'm sorry. I think you're speaking, but
Try another. No. Ah, ok. Eu posso escrever para ela. Tá. Okay. Entendi. Vou dizer.
Rodrigo, será que o volume dela está certo? Desde o volume dela.
okay, but I don't think there's anything from before, and I can hear you when you do the introduction. So that's just weird, because I don't think anything on that time.
Às vezes a saída dela, será que é o fone de ouvido, o telefone de ouvido, né?
You think I can do it the copy?
No. And now?
Yes, I can do it.
So finally, is there any question? No? Okay, so Alberto, please.
Hi, Costanza. When you were talking about the integrability of hydrodynamic systems, I was recalling some work we did a long time ago with Franco Magri, where we were relating the integrability of the reduction of hydrodynamic systems with separability of the corresponding equations and the existence of pencils of recursion operators. I don't know if you are familiar with this work. In any case, the fact that you have there is a relation between integrable in the sense of recursion operators, in the sense of bi-Hamiltonian systems introduced by Franco Magri, and that should this mean that there is a hidden structure in the space and the ensemble?
I would expect there would be a bi-Hamiltonian structure. For other example of integrable chains, well-known examples of any chain, indeed the Gaussian structure has been studied, but we haven't gone down that route. I would expect that to hold. I wouldn't know how to go about it.
Okay.
But I would expect that to hold.
Okay. And finally, have you explored other? I'm not currently. With the literature and the work on ensembles of matrices, but beyond the unitary and symmetric, for instance, is there people that would explore other ensembles, like for instance symplectic or Hamiltonian matrices? And
so there is definitely work of symplectic matrices, and the interesting thing about the symplectic matrices is that the underlying integrable structure is given by the path lattice. So it might mean that part of what we do for the SME can actually be, replicated for the symplectic matrices, because it's the same integrable structure. So in principle, I don't see any reason why it shouldn't be the same chain, but I guess it would be a different initial condition, just on top of my head. But yes, I'm aware that there is work also on the symplectic case, and also there is work in cases where you have two ensembles together. By that I mean that instead of having some potential trace of M, you have some potential in trace of M1 and M2, and you're integrating twice, and usually that's done with the Hermitian ensemble. So yeah, and I am aware that there is more literature on that. And the point is that there is still a lot of work to do for the SME, because the literature that is there for the SME comes very much from Adler and Van Merbeke, and comes very much from the point of view of orthogonal polynomials, which is something that we have been using, but still not in terms of these hydrodynamic systems. Okay. So that's something that we're trying to develop.
Okay, well, thank you very much.
Thank you.
So, any more question or comment? No. So, Costanza, thank you for your participation, and next time maybe in person here in São Paulo.
Next time, I do hope to manage to come in person. And thank you for your patience with the technical issues, everyone.
Okay. See you. Bye. Bye.
Okay. Bye.
Perfect. Thank you. Welcome back from the lunch session. So it's my pleasure to introduce the first talk after lunch, which is Pieter Naaijkens, who will talk about ground states of Kitaev's quantum double model in the thermodynamic limit.
Thank you very much. And of course, I also like to thank the organizer for the invitation to give a talk here. It's my first time in Brazil and in South America, for that matter. So I'm very excited to be here, and it's been very interesting already this week. Yeah, so I'm going to talk today about, it's a bit of an older paper. It's actually the first time that I'm going to talk about this paper, so yeah, that's nice, but if my slides are, there's still some errors in there, then that's the reason. But towards the end, I will try to mention some new stuff. So I have a new paper out on the archive just today. So I hope to advertise that at the end. It's only vaguely connected to this, but you know, I need a reason to advertise that. So I first want to start with a little bit about the sort of the background of the kind of thing I'm interested in. So I'm interested in the classification of gapped quantum phases. So, you know, pictorially, we have some Hamiltonian with a ground state, and it has a spectral gap. Well, with the spectrum, there's no spectrum 0, and some positive gamma, of course. Right, so that's, so two states are in the same phase if they're connected by a continuous path of gapped Hamiltonians. This in itself is not really so interesting, but so usually you want the Hamiltonians to have some other properties. So in our case, you want them to be local, to act locally. Right, so that won't play too much of a role in this talk, but it's just sort of the setting that I'm interested in.
Are you assuming simplicity of the constraint?
No, at the moment not. No, I'm not assuming anything. So the kind of models that I'm interested in are these so-called topologically ordered ones. So these are quantum phases of matter. So quantum phase of matter is basically just a quantum ground state. So, but they don't fit into this Landau theory of symmetry breaking. So they were discovered quite some time already. There's not really a clear definition of what's a topologically ordered model. There are lots of examples, but not really a clear definition. But some features that we have there is that a ground space degeneracy, depending on the topology, so we will see an example of this later. But this kind of models, they have, so you can define them on a compact surface, and then the dimension of the ground state space will depend on the genus of the surface. And the models that I'm interested in, they have a property called the long-range entanglement. I won't be talking about this today, but it basically means that it's sort of far away from product states, so very quantum. And one thing I'm particularly interested in is that these models, they have excitations which are anyons. So unlike bosons and fermions, if you have two anyons and you interchange them, you get a complex phase for abelian anyons, so not just a plus or a minus, or some non-abelian operation. So that's kind of why so these are applications to quantum computing, so that's kind of why I got into this originally. But that's the kind of things I'm interested in. And these models also have a bulk boundary correspondence, so if I have some time at the end, I will say a bit more about that. Right, so what I will do in today's talk, so I will talk about Kitaev quantum double models, which is sort of a prototypical example of these topologically ordered models. So I will introduce this model, and basically the main part of my talk is, what I'm going to talk about is the ground states of this model, but now not on a compact surface, but I'm going to look at them in the thermodynamic limit, so in a 2D system. So I'm only talking about systems in 2D today. And towards the end, I will say a little bit about bulk boundary in this setting. All right, so let me introduce the model. So I'm going to assume G is a finite group, and I have some graph, oriented graph, and you should think of this as this being embedded into a surface, or later for us it will be just in the plane, so Z2. So I've drawn a square lattice here, but you can basically do any oriented graph. And yeah, so we have this orientation here. So in the Iberian case, so most of my talk I will talk about the Iberian case. The orientation doesn't matter, but in the non-Iberian case it does. All right, so what's the model? Well, on each of these edges here, I have some G-spin, so I have a quantum system that's described by this Hilbert space, just finite group, so it's just basically the group algebra. All right, so that's the model. So to define the model, I have to define the dynamics, and to do this, I have to define some operators. So these are called star and paquette operators. So this is a star, so just for these edges incident into a single vertex. And for each of my group elements, I can define an operator like this. I can choose a basis of my four edges here. So I choose a basis element here, so this is an elementary tensor, this is the tensor product of all these basis vectors corresponding to this. Then I define an operator acting on this thing by this way. So if this edge goes out of the vertex, I multiply on the left with G. If it goes in there, I multiply on the right with G inverse. So I will use the notation G bar for the inverse here. So that's one kind of operator, and the other one is if I have a phase or a paquette, I can right. So I have to choose a. I forgot to indicate it here, but I have to choose one of the edges where I start. So again, I have this kind of basis vector, and this operator is defined as this projection. So I start in the so where do I start in this case? I start in the upper left corner, and I go in a counterclockwise way. I multiply all these group elements. So if I go against the direction, I take the inverse, and if I go in the same direction, I take the group element itself. So if I do that, I get this thing here, and if this is equal to h, then yeah, so that's just the delta function. So if it's equal to h, I get the same thing back, and otherwise it's going to be 0. So this is a projection. Right, so if this h is in the center, it doesn't really matter where you start, but if it's not in the center, it does matter. All right, so this is, if you maybe you've seen some lattice gauge theory or something like this is the flux to a paquette, so we can think of this as some kind of a magnetic charge. All right, so what's my Hamiltonian going to be? For each v, so v is the vertex here, I have this corresponding operator here, and I just take the average over all the group elements. So what this does is this projects onto the subspace that transforms trivially according to this representation. I just take the average here. And the other term is very easy. I only keep the paquettes here if I do this product here, if I get the identity element. So E is the identity element of my group. Right, so there's some properties that we can check. So these commute with each other. It's not immediately obvious, but essentially what you can see from this definition here, you get here on one side you get the G, and otherwise you get a G inverse. So if you take this product here, these things will cancel each other. Right, so if it's non-Abelian, you have to take the sum here, but here then it works out. But you can check this, so these commute if they act on different sides, on different vertices, and if they act on different paquettes. So these are going to be the terms in my Hamiltonian. So what's the setting here now? We have, so this is, the C2 is for the Tor code, so that's sort of the easiest example when the group G is Z2. So we have these paquette operators and the star operators. So what's my Hamiltonian? I look at these things. So these operators are projections, and so 1 minus this thing is also a projection, and this is my Hamiltonian. And then the ground state in the finite setting will be any vector that satisfies this property. So these all have eigenvalue plus or minus 1, this AV in the PP. Sorry, in the definition that I have 0 or 1. So yeah, that's basically two conventions for the Tor code and all the other models. But yeah. This graph, you mean? Yeah. So basically, the way I think about this is on each edge, I have a quantum system sitting with a G spin, so it's a G-dimensional Hilbert space, and so this operator here acts on these four just on the tensor product of these four things. That's, yeah, and here's the same for this. Yeah. Right. So yeah, any ground state you will see from this. So these are all projections. So this if you have a vector like this, it has that eigenvalue 0. So it's a ground state. This is a positive operator. So it looks very simple, of course, because all these terms commute in the Hamiltonian, so we can actually exactly solve this. And as I said earlier, if we define this model on a compact surface, so let's say on a torus, so you take periodic boundary conditions, then you get a four-dimensional ground space for the Tor code, so G is set to, and so it depends on the thing. So if you define it on the sphere, so G is 0, you only get one ground state. So one of the features of these states, and that's not really obvious. That's something that you have to prove. But it's that they are locally indistinguishable, and that's sort of why these things became important for quantum information theory. So what does it mean, locally indistinguishable? That means if I take an observable that only acts on the part of the surface that's sort of small compared to the whole system, then all these ground states will give the same expectation values. So the only way to go from one ground state to the other, people seem to have trouble opening the door. So the only way to go from one ground state to the other is to do an operation that sort of goes like a non-local one that sort of goes, in this case of the torus, it goes like you have to go like around the torus in this way or this way. So now you can maybe already see where this dimension 4 things comes from. So that's sort of a pictorial thing. So as I said in my title, I want to talk about this model in the thermodynamic limit. So what I'm going to do now is I have my same lattice, but now it's just infinitely largest in Z2. So this is the Z2 lattice, but my spins don't live on the vertices, but on the edges between them. So how do we describe this? Well, we've already seen this a few times. So I work in the C-star algebraic framework. So what do I have? I have local algebras. I can just take a finite number of edges. And of course, the algebra then is just the tensor product of these matrix algebras. And my D here is just the dimension of the edges of the space on the edges. So it's so in our case it's actually the size of the group. Right. So these have a very nice structure. If I have one finite set, I can embed it into a bigger set. These algebras embed very nicely by just tensoring with the identity on everything that I add. And it's local, so if I have two disjoint sets and I see them as part of a bigger set, then they will commute with each other because they act on different tensor factors. But anyway, from the first part, what I said, we get an inductive system, so we can take the inductive limit, and that's what I call the quasi-local algebra. So this is really physically the way to think about this. It's all operations that you can approximate in norm by acting just on a finite part of the system. Right. So this is all standard material from Robinson. Many of you have probably read that. But yeah, so then we still have our local Hamiltonians. But of course now our Hamiltonian itself, there's no Hamiltonian of the whole system in the C-star algebra because you have to take an infinite sum. So that's not going to live in the C-star algebra. But anyway, these Hamiltonians, they give dynamics. So they give a time evolution, so one parameter group of automorphisms, and we can define ground states. So I will have them on the next slide. So before I talked about this, that ultimately I'm interested in these gapped phases of matter. So when do I say that the system is gapped? Well, you can show if you have a ground state omega. You can do the GNS construction, so we've already seen this a few times. And in the GNS construction, you can define a Hamiltonian H, so it's going to be an unbounded operator. So if this Hamiltonian has a spectral gap above 0, then we say the system is gapped. Right. So how do we define ground states? So yesterday we saw a definition of ground states. That was different than the one I'm going to present now, but it's equivalent to this one. That you can also find it with Larry Robertson. So I'm going to define it to a derivation. I have my local Hamiltonians here. I take a local observable, so A only acts on a finite part of the system. And then I can define this limit here. And, well, this converges because of the, these terms in the Hamiltonian, they only act locally. So all the terms that are outside of the support of A, the commutator is 0, so if you just this thing just becomes constant at some point. But you cannot define it for anything in the quasi-local algebra for something that's not local, this might not be defined. Alright, so this generates the dynamics. So you can use fancy techniques like Lee-Robertson bound, but in this case it's actually, because all the terms in Hamiltonian commute, you can actually just write out the exponents and you get an automorph. That's very easy to check. So it's basically e to the power t delta, or yes, t delta. There's basically two conventions. So some people put the I here, not here, but in the exponent, and some people do it just the other way around. So we'll have to be careful. Right. So what's the ground state? So a ground state for a state, well, for this H lambda. So we have now this family of Hamiltonians, and if omega satisfies this criterion, so minus I times omega A star delta of A is bigger than 0 for all A in the domain of the derivation, then we have a ground state. So this is really just saying this is really just positive energy condition if you start to if you write it out. So this tells you that you cannot lower the energy. Right. So so if you have a state that satisfies this property, as I said before, you can get back your Hamiltonian in the GNS representation, and the GNS vector will have eigenvalue 0 for this Hamiltonian and so on. All right. So yeah. So I'm going to write K for the set of ground states. So the goal for my talk is basically to characterize K in the case of the quantum double model. So I will mostly talk about the abelian quantum double model, so that's where our group G is abelian. And towards the end, I will say a little bit about the non-abelian case. Right. Yes?
It's possible that if you took a different ground state, you get a different Hamiltonian.
I mean, I think that's a different question. You know, you can always take a state and ask, is there a Hamiltonian that has this state as a ground state?
Sure. Taking one state and taking a Hamiltonian that depends on the state.
No. Oh, you mean in the GNS representation? So your question is?
The last line says you can look at the set of ground states.
Yes.
Or that you took a different ground state, you get a different.
Yes. So yes, they can live in inequivalent representations basically. So yeah, that's actually what's happening. This is so I see this as a family of things. So yeah, so for every finite set, I have defined a Hamiltonian. Yeah. Thanks. Right. Yeah. So the idea is to characterize this set K of ground states. Right. So we have this little lemma here. So remember before we had this ground state was a state where that was stabilized by this AS and this BP. So if you write this in in the C star algebra picture, so now my state is a linear functional. You can still look at states that have this property. And if we have a state that has a property, it is a ground state in our definition. So for example, we would have to calculate terms like this, or with the BP, and well, this is just writing out the thing. So this is this Cauchy-Schwarz inequality, yeah, this is positive. Right. So what you can show, I forgot to mention this here. So actually, if you have this property and this is bounded from above by the unit operator, then this thing is actually the same as without AS. So you can put in AS or the BP on the left or the right, and get rid of that. So you can just forget about this one, and this is positive then because omega is a state, and this is positive because so this is smaller than this one. Right. So there's a lemma. There's actually only one state that has this property, right? So existence of this state, that's sort of easy to see. This AS and this BP, they all commute. They have eigenvalues 0 or 1, so you can basically think them as two independent Ising systems. So you just take a state with all the spins up. So that's defined on this Abelian subalgebra, and then you use Hahn-Banach to extend it to the whole thing. So that will give you a state, and by this it's a ground state. But what's not obvious, and this really depends on the model, is that there's actually only one state that has this property. So there's a unique extension, and yeah, so this was first shown by Ariski, Fanus, and Orodetsky for the Tor code, and we later generalized it. Right, so what does it imply? So there's a unique translation invariant ground state, the state I just defined is translation invariant. It's a pure state that essentially follows from the uniqueness. It's frustration free. So what does it mean, frustration free? It minimizes, so the Hamiltonian is a sum of different terms, and it minimizes each of these terms individually. So it has expectation value, the energy is 0 on each of them individually. So that's quite a special case for quantum systems, and this is basically the only models that you really can handle explicitly. So for us, it's a good thing. And this Hamiltonian has a spectral gap. So you can see that I guess you can already believe that because my Hamiltonian is basically a sum of projections. So you would expect eigenvalues will be basically the integers. Right. So we have now a unique translation invariant ground state. So the uniqueness applies to translation invariant, or also frustration free. That's the same thing in this case. But we can ask, are there maybe other ground states that are not frustration free, that don't minimize each of the things individually? Because, well, you can see, let me just go back to the definition here, where I have it, to find all the ground states, it's not really easy, because, well, you have to do this, well, first of all, you have to choose some state, and then you have to check this condition, which is generally very hard. Right, so, yeah, non-frustration free ground states. So here's my model again. In the Tor code, usually we use this thing, so you can, it's basically the operators I defined earlier, this BP and this, sorry, the thing got cancelled there, but up to adding a multiple of the identity. Anyway, so for the Tor code, G is 2, you can identify them with these Pauli operators, sigma x acting here, and sigma z acting on this one. So these are the same operators as before, up to a normalization. Then we can look at this kind of operators. So I take a path on my letters. Everywhere I act with the sigma x. And what you can see is, well, this thing commutes, of course, with all of these things, because they're all sigma x's everywhere. But with this one, so either I have, if I take, let's say, this star over here, then I get an anti-commutation, because there's only one edge where this one acts. I act here with the sigma x, and I act there with the sigma z. These anti-commute, so I get an anti-commutation. But if I take a star here, I have two of these things, so 2 times anti-commuting is commuting. So here, it commutes with this star, for example, and with this one, because there's always an even number of edges in common. So what we see is this operator commutes with all terms in the Hamiltonian, except for the one associated to this star and to this star. And there the sign flips, so remember in the Hamiltonian you had 1 minus AS, so that becomes 1 plus AS if I commute. So we see we have some energy sitting here, energy 2, and some energy over there. So we can see these things as excitations. And I can do something similar if I take a path on the dual lattice and act with sigma z. Right, so these are my excitations in the model. And now it becomes important that I have an infinite system. Right, so we see we always create pairs of excitations. So I can bring this back and then the whole thing disappears. But otherwise, you can only create pairs of excitations. And this is really a charge conservation. Right, so but in the infinite limit, what I can do is I can take some path that goes to infinity. So the idea is I create a pair of excitation and I move one off to infinity. That's the idea here. So I take a finite path, I have my excitations, and then I take this limit here. So these are this operator I defined earlier. So I just take an infinite path, and psi of n is the first n parts. And you can see that this limit, this exists. That's easy to see if you take a local observable. Essentially, you add things outside of the support, and then this endpoint cancels each other. Right, so that's easy to see in the Tor code because there, well, these things all square to the identity. Right, so we can now look at I have my translation invariant ground state. That is I call omega 0 from now on. I compose it with this map. So what is this? What is this? It is an excitation. Well, it's a state that describes a single excitation sitting at the endpoint and the other one going to the. Right, so there's something about the representation, GNS representation, but we don't need this now. Right, so I said, well, we have this excitation here, but my claim is actually these states are ground states. So that sounds a bit strange maybe at first. Right, because we have here at the endpoint, certainly the excitation value of the Hamiltonian is bigger because we have this anti-commutation thing. However, I cannot decrease the total energy of the system with a local operator. So the only thing I can do with a local operator is I can move this excitation around, but I cannot get rid of it. Because to get rid of it, I have to move it all the way to infinity, and that's a non-local operation. Right, so I can decrease the energy in a small part of the system, but it gets moved to another part of the system. So the total energy doesn't change. So this is why, well, it's maybe not, so that's sort of the heuristic why these things are ground states. So that's what I just said. All right, so that was for the toric code. We can generalize this. So from now on, I'm going to assume being in groups. This is the dual of the group, so that is the characters, and this is the group itself. So we take some pair in the dual group and in the group itself. And to each of these pairs, we can define a ribbon operator as before. So before I just had this part or a dual part. So for these things, I have to take them both at the same time, essentially like this. So that's sort of the picture. But I can define this operator for each of these things. All right, so that's the ribbon operator. And the interpretation is again, you can do a similar thing as before, but the interpretation is this creates a charge at this endpoint here. So this bracket together with this vertex here, and these charges are labeled by this character and by this group element. So this one creates an excitation here and a conjugate excitation here. So in this case, the conjugate is just you take the complex conjugate of the character and you take the inverse of the group element. Right, and we can define these states as before, so it's a bit more tricky to show that this converges, so that uses properties of the ribbon operators. I don't want to go into that, but the idea is you can still do the same thing. You can create this pair of excitations and send one off to infinity. So what's now our theorem? If I have a ground state, then I can find a convex decomposition of my ground state in this form. So these are just positive real numbers that sum up to 1, and this states omega chi of c are in this set k of chi of c. So I'm going to define this set later, but you can think of these things as the set of ground states that have this total charge given by this pair of elements. Right, so we can show a bit more. So each of these k is a phase, and every pure state in this set is actually one of these, it's equivalent to one of these states that I just defined where I go to infinity. So all the pure states are of that form. So when I say that the state is unitary equivalent to this state, I mean that if I take the GNS representation, the two GNS representations are unitary equivalent. And I did not mention this here, but so these sets, they are actually disjoint, right? So if you have a set, if you have a state in this one, it's not equivalent to a state in the k of chi of c for a different pair of k of chi of c. So to coming back to the question earlier, that basically means that they live in different representations of the algebra, different Hilbert spaces, if you want. Right. So I want to sketch the proof a little bit. So I'm not going to give full detail. Yeah. So actually, I should say with who I did this work. So Matthew Chia. So at the time he was a PhD student of Bruno Nachtigaal at UC Davis. I was doing a postdoc at UC Davis at the time when we did this paper. So here's the reference. Right. So what's the sketch of the proof? Well, the idea is essentially so we're going to look at we're going to add boundary conditions to our Hamiltonian. So we have this little lemma. So suppose we have a sequence of operators. So a different Hamiltonian, but that gives the same derivation if L goes to infinity. So we can think of we take a finite part of the system, we add a boundary term to it on this finite part, and then we grow this part bigger and bigger. Right? So if the boundary term only acts on the boundary, you will see at some point it will commute with this A. So you can imagine that you get the same dynamics as before, because the boundary term will just commute with any local operator. All right, so we have a sequence like this, and we have a state that minimizes all these things. So that's a 0. Right, so this is a positive operator, so this has to be 0 or bigger. But if it's 0 for all of them, then it is a ground state. So the idea is for the states, we're going to define we're going to choose suitable boundary terms so that we can verify this. That's the essential idea. And then we send the boundary to infinity. All right, so how do we do that? Well, we've seen before, if we have a charge here, we get some energy there. You want the energy to be 0. So what we want to do is we want to have a boundary term that sort of detects this charge sitting inside, and then we can subtract this energy again. That's essentially the idea. So here we have a charge, gives you energy 2, and then we subtract some term to get back to 0. And of course, you have to show that it's still a positive operator then. So if we just take these things that these ribbon operators have defined, well, what I can do is I can just take a ribbon that is just a closed loop. So you can think of these things as Wilson loops if you've heard about these things. And so we can look at the operators like this, h of L minus some factor that depends on this thing times this closed ribbon operator. So we look at this operator. So this is our original Hamiltonian, and every time there's an excitation of this type chi of c inside here, we subtract this excitation. So if it goes outside of there, it will go back to 0. All right, so of course we still have to show that if you want to apply a lemma, we have to show that this is still a positive operator. So we have some positive operator here, but we're subtracting something. So this is potentially not a positive operator anymore. But with some work, you can actually show that it's still positive. Right, so this is a way of, if we find states that this is 0, we can find new ground states. All right, so so that's one way of detecting this. It's not immediately obvious that this works. So there's also properties of the ribbon operator behind there, but that's true. But there's also a different way of looking at these things. Right, so what can we do? We can take a star as before, and this operator in the Hamiltonian, it was the projection onto the trivial representation essentially, but we can take a different representation of the group. So in our case, the group was a Beagan, so a different irreducible representation, and we can project onto the irreducible subspace, well, onto the invariant subspace of this representation. That's what this thing does. And similar, the term in the Hamiltonian projected onto the terms where this bracket had a flux identity, but you can just take a group element C there. So if you project onto so these are both projections, and if you project onto this one and to this one, you project onto the subspace that has an excitation chi and C sitting at that side. So this is what we call an electric excitation. This is an electric excitation. Right, so now we can see at each side, we now know how to say if there's an excitation there, we just project on these subspaces. Can we say something about the total charge? So I can have more than one excitation in my region. So what's the total charge of this? You know, if you have maybe you have somewhere have 3 positons or maybe and 2 electrons, then the total charge will be +1, right? So we can do something like this here. And that's, in the Beagan case, is actually quite nice. So if you want to have the total charge, we just use the group structure. So if we have a charge chi1 C1 sitting somewhere and chi2 C2 sitting somewhere else, and the total charge in the region is just, we multiply these things. So these are characters, so this is again a character. We take the product, and this is again a group element. So yeah, so how can we define the total charge in the region? Well, I want to define a projection. I take some L. So sorry, I should have said that, but I always think about this L. We just have some square thing, and L is just the size of it, something like this. Right. So that's the one that we're going to grow. Right. So yeah. So we have this area. So what we do? Well, we can look at if you want to project onto the subspace that has total charge chi. What we can do, we can project onto, well, we can first look at all configurations such that the total charge is chi. So I just multiply all these things. That should give me the total charge. So for each vertex, I choose a chi I, multiply all of them, and I want to get chi there. So that's the summation there. And this is just a projection onto this specific configuration. So I choose a certain configuration. So I'm saying at each side, I have a charge chi I project onto this subspace, and then I sum over all the different configurations that give the total charge of this chi. And I can do the same thing with the other one. And it turns out that actually, if you look at these things, so these act on the whole box, right? So for each of my sides in the box, I have something acting there. But it turns out if you do the summation here, all the terms in the middle cancel, and the only thing that you're left with is this operator that acts on the boundary that I defined before. So that went along the boundary in this loop. Right. So that's a bit of work to show that. That's far from trivial. But the useful thing is that we have sort of a very local way of looking at these things and a sort of very global way. And both of them are sort of important in the proof. Right. So, yeah, so this allows for an explicit description of the local ground state. So we can, if you just, cut off the rest of the system, we just look at this finite part, we can decompose all the ground states in different sectors using these things. Right. So that's essentially behind the idea. So now I can define my set K of chi C. that I had earlier in my theorem. So how is this defined? Well, I take a ground state, so I'm going to assume that the expectation value of this thing is bigger than 0. So I just try to convince you that this operator should measure the total charge. So saying that this is bigger than 0, this means that in this state there is some charge of type chi c if I go to infinity. This is just the expectation value of the charge. Right, so I take a charge that's like this, and I look at the state at this state. So I take weak star limits of states like this. So essentially what I'm doing here is I'm projecting onto this specific subspace of this specific charge. Right, so it's not immediately obvious that this is a state, but because of this locality thing that they said earlier, this is actually defined as a state. All right, so that's the set K of chi c, and we can show that it's a phase. Right, so that's my set K of chi c, and as I said before, my claim is essentially that if I go over all the chi and c, I get everything. So the first thing that we want to show is that, well, actually, all the states are sort of contained in at least one of these. So what we can show, so we have this limit here, so here I'm just assuming that this limit exists. But what we can show is that if you take a ground state, then this limit actually always exists. So it can be 0, but it does exist. So that's definitely obvious. And moreover, we have this thing that I said before, that these things are disjunct. So yeah, so if I have a state in this K of chi c, then this value is actually 1 in chi of c. That's immediately clear from this definition. But it actually, if I take a different chi of c, so if I want to measure a different charge, I get 0. Right, so each of these states only has the single charge chi of c. That's essentially what they say. Right, so that's let's take the theorem again here. So what we've shown now. So there's a lot of technical details going behind here that I don't have time to explain here. There's but that's essentially the idea. So that's the theorem to get there. All right. So that was for the abelian case. So of course the natural question is, what about non-abelian, right? That's always whenever you give a talk about something abelian, then always the first question of the audience is, what about the non-abelian case? And of course, then yeah. So this is a work in progress with my student Madi Hamdan. Right, so the question, can we get a similar result for G non-abelian? So what are the things that we needed here? We had these ribbon operators, so they, I showed you that, I explained to you that they create these excitations, but the algebraic properties are actually very important in the proof of this theorem. Well, the good thing is we still have these ribbon operators in the non-abelian case. And we can still define this closed loop detecting the charge, and we can still define these local charge projectors. But before I had basically two different types of charge projectors that I could basically treat independently. So one was the chi's and one was the group elements. This is not going to in the non-abelian case. And the composition of charges is also more complicated. And the reason is essentially because, well, you take the dual of a non-abelian group is no longer a group. So we cannot do that anymore. So it turns out that the algebra behind here is described by what's called the quantum double of a finite group. So the Drinfeld quantum double. That's some Hopf algebra. Don't really need to know the details of this, but the point is that the irreducible representations of these things, they are in correspondence with pairs pi of C, where C is a coincidence class of G. So in the abelian case, all the coincidence classes are just 1 point, right? So that's why I just had the group element. but here it can be any conjugate class. And then what you do is you take an element in there, you take the centralizer of this element in the big group, and then you take an irreducible representation pi of the centralizer. So it's quite an evolved construction. Yeah, so if the group is non-abelian, these representations can have dimension bigger than 1. And that's what makes things a lot more complicated for us. So instead of just a single operator for a given charge chi of c that I had before, if I have a non-abelian case, I have to look at these kind of multiplets of ribbon operators. So we have some extra index here that depends on the dimension of the representation. And we still have nice, in the sense that we can write them down, but much more complicated algebraic relations. So you can imagine that the representation theory of finite groups comes in there. All right. So in particular, these maps that I defined earlier, this conjugation, that's not the right thing anymore, because now we have a bunch of these maps for a single charge and not just a single one. So I cannot just conjugate with it, and actually it doesn't even converge anymore. So what you can do is we can look at this thing. All right, so that's maybe a bit mysterious. Why this thing and not something else? So that's good reasons for this, but I don't want to go into that now because it will take me too much time. But you can define something like this, and this is a completely positive map, and this converges. Right. So we can define this for each of these irreducible representations. So this gives me a localized and unital positive map. So it only acts non-trivially sort of near these ribbon operators. Yeah. So what we can show is that if you look at these states, so we still have a unique translation invariant ground state. We can compose this with this positive map. So this is a state again, because this was a unital completely positive map. And so these are ground states of the non-abelian quantum double model. So unlike before, where we had pure states, so these are now vector states, but not pure. Right. So you can see from this already. So this is basically a sum of positive maps. So this already gives you a natural decomposition of your state. Right. So unless if the representation is one-dimensional, they are still pure again. All right. So we have some candidates of ground states. So the conjecture is, and that's something that we're working on, is that again that we sort of have this decomposition into different charged sectors. Right. And there's some other things that we're looking in, but let's see. All right. So yeah, I think I'll have a few more minutes to talk about this bulk boundary correspondence. Right, so these 2D topologically ordered models, so excitations in the bulk, so that's the excitations that I talked about, so we can say much more about them. Yeah, so it's conjectured that they are related to gap boundaries. So what does it mean, a gap boundary? Well, what you can do is you can take a system, so now I define it on the plane, but I can maybe take a half plane and cut it off there, and then the question is, can I put boundary terms on the boundary such that the resulting state is still gapped. That's essentially a gap boundary. And so that's actually quite rigid, and there's lots of structure that you can see this. And essentially the point of this thing is that by looking at the boundary theory, so a 1D theory, you can actually get everything in the bulk. That's sort of what this conjecture is. So our analysis of the ground states is actually an implementation of this idea. So these excitations, as I said before, so these are these anyons that I talked about. I didn't say that explicitly, but yeah, so that's the one that we're interested in. And in our case, essentially what we did is for each type of excitation, we could choose a specific boundary condition that realizes this thing as a ground state. So yeah, so we can see by choosing the right boundary conditions, so by looking at the boundary conditions, we can actually see what kind of excitations we have in the bulk. All right, so that's a very it's a very sort of more heuristic thing. It's not very rigorous. But the very recent work, so that came out on the archive this morning, or yesterday evening, I guess, here. So we have a different approach for this topological order, which we call the extended TKO conditions. All right, so our conditions are satisfied by the Kitaev and Irvine models. So these are sort of the prototypical examples of topological ordered models. And what we can do is we can define a boundary algebra, so an algebra of observables acting only on the boundary, sort of in a local way. So it's not just looking at the states, but we have to look at some corner of this algebra, so to project down on certain space. So we don't need Hamiltonians. But yeah, the point is we can look at states on the boundary, and they automatically extend to states in the bulk that are sort of compatible with the dynamics there. Right, so I would like to, so there's a whole theory there, but I want to pick out one result in particular, because it relates to KMS states, and I know many people here like KMS states. So what we can actually show is that for this Irvine models, so there's a canonical state on the boundary, on this boundary algebra, and this is actually a KMS state. Right. And the corresponding von Neumann algebra is a vector of type 2-1 or of type 3. And so this depends on, so this Irvine models, it has an input. So this is for people that know a little bit about this. So the Irvine models is based, so the input data is a fusion category. So if you have an element in your fusion category that has a dimension bigger than 1, then it's a vector of type 3, and otherwise it's a vector of type 2-1. So that's sort of the thing that we were interested in the type of this vector, which is why we started to look for KMS states. Right, and so we also heard a little bit more about bimodals yesterday, or C-star correspondences. So we have our boundary net, and we have something called DHR bimodals. So these are bimodules that satisfy a certain extra locality condition that's inspired by algebraic field theory. So we can define this category, and this actually has a very nice structure. So this category is the Drinfeld center of this input category C, and that's usually what people mean with bulk boundary correspondence. All right. So if you don't know much about tensor category, they will not say much. But essentially, this is a construction that you can do to build the excitations in the bulk from the excitations on the boundary. All right, and so another result is that that basically follows from the first part, is that so you can look at what's called the cone algebra. So we have an infinite system. We look at a cone like this, and we can look at the GNS representation generated by this thing. So we look at this thing, von Neumann algebra. So that's called the cone algebra, and yeah, so this is type 2 infinity. All right, so yeah, this is the paper that's on the archive there. So that's so if you want to learn more about this, I suggest that you have a look there. And that's the end of my talk. So thanks very much for your attention.
Great. Thank you, Pieter. Does anyone have a quick question? Yes?
Yeah, so in classical statistical mechanics, the important aspect is not only whether you program states, but whether they are stable on your range of states. And typically what happens is that these states where you have local or non-local removable excitation, for instance, the Würzburg condition, they tend to not be stable under temperature, rising the temperature at low dimension. And there is a dimension at which they become stable, so they become physical. My question is whether you can do an analysis of what happens when these are
Yes, that's a very good question, and that's actually so So this is related to, because so originally the idea of these things was to use them for quantum memory, essentially. So there, of course, you want this to, so this is only about ground state. So there you want, you know, a real system is not at 0 temperature, so it's higher temperature. So unfortunately, that's a no-go theorem. So in these 2D systems, you can show as soon as you has a non-zero temperature, basically everything is gone, all the structure. So yeah. Yeah. So yes. So there's no-go theorems in 2D, and I think in higher dimensions it is possible. So there's a higher dimensional analog of this Kitaev model. I'm not sure if people have looked at this already directly, but I think it's believed that in maybe 3D or 4D it actually is. Yeah, that's an interesting structure. Yeah.
Great. Any last very quick question before we move on? In that case, let's thank Pieter once again. And the next talk is Christiaan. Okay, welcome to the second talk after lunch. So it's my pleasure to introduce Christiaan van de Ven, who will talk about classical dynamics of lattice systems in an operator algebraic framework.
So thank you very much, organizers, for this nice conference. It's also the first time here in Brazil and in South America. I'm happy to be here. So today I will talk about a joint work with Irvine working at the moment in Australia. This work is not yet published, not yet on archive. We are about let's take 2 weeks more probably. We face some small problems. So people. So I was speaking about trying to suggest classical dynamics of lattice systems in a greater algebraic framework. First, I situated in Würzburg in Bavaria, the south of Germany, and people about Germany think maybe a bit cold place, it's true, but these are grapes. They are not only in France and Italy, but also in Germany we have this. This could be 50 kilometer walking on here. This is a mine, a river. I would say kind of beautiful, so a good place. Yeah. It's not like a proper like no boundaries there, but it's still a nice place. So, I will give you a small overview about myself. Say something about the motivation, about why we want to do this work. Then I sketch the relevant mathematical framework based on resolving algebras, commutative part of it. Then we go to the classical lattice systems and say how they interplay with those algebras. Let's say some sketch the main results. So we have a proof sketch, basically it's going to give the complete proof. And I can extend this to infinite systems. If you say something about continuity of the relevant dynamics. Then I say something about generalization, how to generalize those. That's basically the problem that we got stuck yet. That's why we couldn't publish it yet. The motivation. So one could think about classical expressions. So think about a spin system, taking values in a discrete or finite set, so plus minus 1 or finite sets. That is an example of what one could think of, right? Another example is one could generalize it a bit more. So in this case, you can say spin system, but the single spins, they could take values, for example, in a space, a compact space. There's also, the classical Heisenberg model is defined in such a way. And in view of this example, it's so spin systems on a compact space. The configuration space is kind of easy because this infinite problem of spheres, the thing Sn or S2, what you want, it's compact. And the algebraic structure, according to these observables there, it's also not that complicated because you have just that the contained function values in infinity are bounded and are contained on this compact product of infinite space. So here is kind of no really problem here to define a theory. Problem arises is to take a general classical data system in which your single side space is not necessarily compact anymore. Think of R2 or R2n. Then the configuration space, what would it be? So in the infinite product, an infinite system, it's not completely clear what you can do there. This omega here, you cannot just put, you can put an infinite product of Rn or R2n with itself, but you have to be really careful to do this. So the algebraic structure becomes observable, so one could take, see this C0 omega. One could say, okay, maybe we can find some omega in the case of the unbounded. One could say, okay, take C0x, but this is trivial if it's an interdimensional vector space, interdimensional vector space. So this also doesn't seem to be the right strategy. So what is the solution to do so? To deal with such systems, lattice systems with unbounded single-sided space. Our method is a mathematical approach. It was worked by Abel, and those people, they proved a lot of nice results in this. Maybe a less known method, but which turns out to work in this case, is an algebraic approach. Can be algebraically solve such a problem. Can we define a dynamics? Can we define a configuration space? Can we get a dynamical system? So that's exactly where the commutative resolvent algebra is coming into play. Before I want to go to this, I will just give you a small overview of the resolvent algebra. So that is maybe more familiar with C-star algebra. It's not commutative, it's more quantum systems. It's basically the resolvent algebra. So it was produced by Google and Grundling in 2008. Google is a German mathematician, and Grundling, I think, too, was working in Australia. So basically what happens, you take a linear space and go to the general spectral form, then you can associate a non-commutative resolvent algebra, given the resolvent operator of the field component. So this is the resolvent you know. You take your lambda, you take lambda out of the real out of the zero, and those phi f, nothing else than fields, possibly unbounded operators satisfy certain relations. So those commutative relations and deals with yourself resolved. Expected then this will be this algebra is a non-commutative C-star algebra invented by, as I said, Google and Grundling, and it's called a resolvent algebra. It's non-commutative. The C-star algebra contains the compact operator as an ideal, which is nice because we see that the commutative resolvent algebra, the one we study, contains its classical counterpart, which is the C0. But that will come later. This algebra, in contrast to the Weil algebra, is highly efficient to model dynamics, quantum systems. The Weil algebra is not really compatible with dynamics of interacting Hamiltonians. So dynamics is not really stable in that Weil algebra. The resolvent algebra instead is very nice to model those things. And Google and Google, I think they always make their own Googles try to prove such stability now, also for the Coulomb potential, which is interesting for study of Bose-Einstein condensation in an infinite system. So this is a really nice algebra to study dynamical systems. But there is also a classical analog of this R of X. That is denoted by this algebra. So you take an infinite real interval space. The commutative resolved algebra on X, which is denoted by CR of X, C of commutative. The unit of C star algebra, subalgebra of the bounded functions on X, generated by the classical resolved in the sense they are just those functions here. So X dot Y is the inner product which is real, so you take lambda, for example, you should take it outside the real, so you take it, you multiply it with a complex number. So then this is the resolvent, the classical resolvent, which is the classical analog directly of the non-commutative one. So the nice thing about this, some properties, is that a dense subalgebra of the CR of X, you see this algebra, this X could be very big, could be very large. Consists of finite number of so-called Debbies. Those are functions given by composition of G times projections, where G lives this S, maybe the Schwarz space, or you could take a compactly supposed full function on a certain finite dimensional subspace of X. So you have this finite dimensional subspace, you project it with this projection, project onto this, and then you consider the composition with a G. And the span of all such functions, they form a dense subspace of your commutative resolvent algebra. So elements of this, you can think of elements for the zero and just the 7 to 0 only in finite dimensional directions, because this V is finite dimensional, and in the other direction, so if you take something orthogonal to it, then this is 0, so you get just G of 0, so it just gets a constant in the whole of perpendicular direction. But that's how you should think about this this algebra, this subalgebra. So we have also this that continuous functions values of infinity of X are included, this strict inclusion in the commutative resolved algebra, which is in turn included in all the bounded operators. So finite and infinite dimensional X. The nice property about this algebra is not this. It's that it is the C star of the inductive limit of the next CR V. So you take all those sequence of finite dimensional. You take a sequence of those in CR V or V ranges through X as finite dimensional subspaces. And you have to say how do you make some limit? You have to say something about the connected maps. So the pullback of the projections. And this is kind of nice because if you see that this X could be infinite dimensional, you see how it arises. So this is kind of a thermodynamic limit procedure. How it arises from finite dimensional parts. But it's very nice if you want to study a thermodynamic limit. The same model.
Describe the spectrum of CRX.
That is what Teun has described this. I don't know exactly how it works, but he described this in this paper where he just studied this commutative resolved algebra, where he studied, I can send you if you want to, he studied all those things about it. But also need to double check, I think, something. It's not that easy. The point is here that if you think about the quasi-local algebra Pieter just described, there's also an inductive limit of local observable. Think about it in the same way. So it's nice to study thermodynamic limits. And
if V is finite dimensional, you want to simply get sigma of V.
Yeah. And then exactly. So and on the direction orthogonal to it, you get just a constant.
So if X is finite dimensional.
Yeah.
You get C naught of X.
Yeah. So those are some properties of this commutative resolved algebra, and this property indicates whether it could be interesting for thermodynamic limits properties with it. And that's exactly what we're now going to do. So we're going to consider a classical data system. You take a discrete subset gamma of RD, so this gamma could be infinite dimensional in general. So this should be the lattice. So it could be a cubic lattice, but not necessarily. It could be a discrete subset. And if you then take so a fixed lattice point in gamma, then we can associate it to all single-side phase space which is infinite dimension R to N, as being this space. So this LC indicates finitely many sequences. So finitely many sequences which are, you know, right? I don't know how to explain this. So compactly supported sequence, basically, which are non-zero, only infinitely many entries. So this decomposes in such a way. So this, you should think about this. Impulse direction. So the momentum, the R2N, and the other one, the Q, the position. Probably did a mistake. Yeah. Okay, but this. Anyway, the idea is clear, right? So this is our configuration space. It's countably infinite dimensional vector space. We can equip it with an inner product, just go one from L of 2. That is our configuration space. So we take the sequences, at some point, just F6. Then we can define any, this means finite subset of gamma, because gamma would be infinite in theory. We can define the configuration space just located in lambda. This is omega lambda, consisting of all points in omega which are 0 outside lambda. Okay, and that is also indicated as isomorphic to R2 and N, right? Because this is 2 N and we take to L lambda points inside. So again, see that this omega can be written in this way, and CR omega is the inductive limit of those omega lambda. So you really view now your vector space omega as a limit of those lambdas here. And that's net CR omega lambda if you take the inductive limit. And then we also want to say something about the Poisson structure, right? Because we have here R2N as a symplectic structure, so Poisson structure in general, in particular. So you can, for such two levies, in this dense subspace, you can choose lambda large enough, and then you can define your bracket in this way. So this is it's clear, right? So you take those two levies, and your bracket is then just you compose, so this the pullback of P omega lambda with this bracket on the lambda. That's what you basically do, and that gives you a well-defined, you can prove those things, a well-defined Poisson bracket, so that indicates that you have a classical theory with a bracket on top. But that's basically what I want to say about the classical lattice system. Now we go to the Hamiltonian. So we have such a setup, and now we want to view some Hamiltonians compatible with the setup. So we take this Hamiltonian, so this takes all finite lambda subset of gamma, then we write it, but we take then all the finite, so lambda is finite, so all the subsets, the general definition of it is the potential phi of b, and then you have to say what this potential exactly is. Let's choose to be this here. So if b is a singleton in lambda, then it is just this, you see it is the free part, the impulse part, and this is the untrapped, the harmonic part. So if you just consider the first line here, you see a harmonic oscillator, a simple harmonic oscillator. The mass, each mass, and a harmonic part. But we want to add also a potential, otherwise it's a bit simple. So we add a certain potential here. If B is so set consists of two elements, not necessarily nearest neighbors. And V, of course, should satisfy some properties. So we have this property, the first property. You should think about it, for example, if you V, K, L, you can see this J, K minus L, VH. So this J is models the interaction strength between the several particles. But this could be a nearest neighbor interaction, but we just don't say it. We take arbitrary interactions. We just assume the following things that on those V that it is values on infinity on this differentiable each KL in your lattice that is Lipschitz continuous. This is an important property to a unique flow, And we have this summability relation that the gradient is supremable and summable, and then you have also take the sum before. It's maybe a bit strong, but in the case of if you have a nearest neighbors, then this is also often asked by people as French. I don't remember, but this is a condition that we often encounter. So this is then the Hamiltonian, the potential, the assumptions. So we have to take, we took a specific free boundary conditions, right? Because we don't consider intersections with lambda and other parts in gamma. We just consider really subsets of lambda. But that is not a really problem. One could think why you don't take general interactions, so general subsets here, but have non-zero intersection with lambda. Because we're considering a thermodynamic limit, and then the idea is that in the limit, so the dynamics, this boundary kind of disappears out of the limit. So that's why we took it a free one.
But they could be pathological conditions.
Yeah.
Because they are bounded and they could grow as you move out.
That's true. If you take strange boundary conditions here, for example, then the first point you see is that if you, on the lambda itself, so on your finite system, your system is not preserved because you always the lambda is not preserved because due to this boundary you add up new terms always. You exit always, so the flow is not preserved and then nothing is preserved. So we cannot do this because we first thought to do it like that, but then the flow is not the phase split on the lambda is not preserved under the flow because your vector field is not preserved if you add this extra boundary interacting with it. And so we really have to do it like this. And what we can see directly from this formula 1 is you can decompose a lambda in a harmonic, let's say a simple harmonic oscillator, which is just this, plus a potential, this potential. And the idea is now to prove stability, that we deduce properties of this here, use the very well known properties of the harmonic oscillator, and then compare them with the properties of this potential. So that's what we call time stability for finite systems. So we have a lambda fixed subset of gamma, finite. So all the assumptions on the potential, they enter that the Picard-Needler theorem is valid. So you get a unique flow of your Hamiltonian system. So XH is the Hamiltonian vector field induced by the Hamiltonian. So the P dot Q dot is minus the the nabla Q. So just those really well with those equations with this first condition. So P0 Q0 is just a P naught Q naught. So and time evolution is done giving this, having this unique flow, and nothing else than this method, which is a homomorphism corresponds to the flow of your vector field. And this is unique. So to connect this to an algebra setting, it's just a matter of notation, right? Because this is a flow. We want to see how this acts on observables. So for any fixed f, you commute it with resultant algebra, you find then the algebraic term, we need to count algebraic because it is related to the function. It's the payback of the flow of this function f. And maybe a more useful notation that people also use is just the alpha. So the alpha is the automorphism acting on this t fixed. So that is then the setup for our system. We have this flow, we have this setup. The next question is, so it is a specific case, because we still have some problems in the case that if the masses are not equal and the force constants, we call those mu's, are not the same, then we can encounter some problems. At the end of the presentation, I will say something about this. So let's first assume that it is all equal. So the system is the same, but every particle has the same mass and the same constant force constant. Then it's relatively easy to see. It's not that easy, but you can prove that the flow indeed preserves this algebra, finite lambda. So the proof sketch is kind of because there's 3 steps. We consider first the case that your potential is 0. That we need this result after for the next result. What you basically have then, you are left with just a simple harmonic oscillator. And this system is integrable, so you have to argue the revealed theorem. This decomposes just into n harmonic oscillators. But each of them, each of this harmonic oscillator, simple harmonic oscillator, lives on Rn. So that's the idea is done that the flow splits into n flows. But okay, each particle of each system is of dimension small, so we have to reduce it further to get really a flow so a particle of one dimension, but phase space R2. And that is just the idea to reduce the flow, which is possible, because here there's no interaction here. And what you get is just apply the already revealed theorem again. And then you get some n subsystems of dimension 1, and then the flow is just given by rotations, simple harmonic oscillator rotations. And the frequency is then this number, which is, of course, in this case easy because this nu and the n's are all fixed. And it's not, if they are different, then you get interaction, different speeds, you have to work a bit more. So, and then it's clear, a rotation, so a composition of rotations, and as any levy is central rotation, it happens nothing, it's again a levy, and then it's clear that the levies are preserved in this flow, and therefore, since they are dense, the result follows. You have stability in case of simple harmonic oscillator. Second thing now is, if you now take potential, not C0, but you take compactly supported for all K and L and lambda. It's the second idea. So what we do, this is maybe a bit technical, we write here pos moments, so the position and the momentum. So P, QL pos X the configuration, just projection QK minus QL. That is the Q coordinate, so that's why pos, position. And the momentum is the same, and then you have the P coordinates. We then introduce this potential, which is a bit more general. You consider here all so sets in N, so two sets with two elements in N, which they are not the same, K and L not the same. This is a particular case of the potential we want to consider, so V lambda, so if you take lambda in particular, then you get exactly the potential we have. Why we do this? Why we generalize this potential in some sense? Because in order to prove this theorem, you need an induction argument, and then you want to induction on the side of this end, and then it's really important to have this a bit more general. So that is basically what you have to define. You have this potential, and then you consider the Hamiltonians defined according to this Vn, right? So A lambda 0 is of course the same, because then it's a simple harmonic oscillator. Hn is A lambda 0 plus, instead of V lambda, we take now Vn, find Vn. And we take another one, An minus Kl is defined as n, but you put out 1. So it's this one, but you just take out one fixed Kl. So it is, you see what that means, it's just An minus Vkl, you see this, Vkl, this would be a pos. So that you just put out 1, and that's a very important thing to do induction, which we see later. And then you have those flows, you call the flow omega 0 is the flow corresponding to this symbol link. Omega t is the flow we want, Hn, system VB1. And omega tilde is the flow corresponding to the one without left out one subset. Having done this, we can now get proof of the theorem in a case that potential is compactly supported. So you define a minimum period, the quarter period. So if you take about a rotation, so the circle, then you have this rotation, right? So we are interested in, if it goes this way, in the time from here to here. Of course, there are some constants of m, the square root of m divided by u, but that is not really important. So the period is 2 pi, we are interested basically in this first part. And then we take, so this is, let's say, if you take this constant to 0 with the scaling, you call this time t min is just the first half pi. Then the idea is that if you prove this theorem for a fixed t within this 0 to t minus, then you are done basically, because you can take powers, because it's the inverse. You can just do it like this. You get everything. You can take this inclusion is because of this power here. And if you, by taking the inverse, you get the one inclusion. That means that you get also really identity of the so really preserves the result. It's not inclusion, but just equality. But the idea is to do it for this specific t inside this first quadrant. The proposition is this. This is a bit technical, but it's kind of nice, because if you fix such an element in your n, so set consists of two elements, and you take an arbitrary time in that interval here, right? So the time inside here, somewhere here. Then for all delta, you can take there is a number. So that if you have this norm is large enough, then the two flows. So this is the flow corresponding to the system, and this is the one without one element. They kind of become very small. And how you see this, to prove it, give you a small sketch about this proof. This I need one second. So what you do, you basically, maybe it seems not that easy, but it is kind of easy if you have the picture in mind. So you have this is my circle, my rotation. This is for, let's say it's the QL minus QK with L direction, and here's maybe the support the potential. Let's say it's somewhere here. So if you then look, this is the part. This is the time here. Okay. The idea is that if you take this node, this PKL post 1, if you see what is it, this is just the energy, the total energy of your system, right? Because there was check. This is related to the energy of your system, and that is not depending on time. So the idea is to get a very high energy, so that this goes very quick, particle moves very quick. The time it really sees the support here, so the time that is really inside this support is very small. That's the idea. So in that very small time, it gets epsilon small. This time could be made, time it passes this area, let's say, could be so small that basically that is kind of all the epsilon. So that is this idea. And in the time that it is outside this interval, so we then define a ball, so take Q up at n, for which holds that the distance between this Q and the support of this this one potential VKL, this should be smaller than a certain number. Just explain what this number is. You then define a first time interval, it's basically the inf of all times such that right now. So this corresponds to the flow of the unperturbed system, the harmonic oscillator. Is exactly in this, so we call it P, K, L, called image, so pre-image. So this means, so the omega, so the code means you project onto the Q coordinates, onto the coordinates. This is the first time the particle, the unperturbed particle, so the harmonic oscillator, this zero indicator, enters this, so basically enters the support, it comes close to it goes here. The first part, it goes here. You can do a similar thing here for the sub, so T1 is basically a similar thing, but then you take here a sub, and then you have a similar here. That's the time it exits, so it's T1. Basically, you see it exits the support. Okay? That you can do. And outside of those two times, if you are just so you have to give you an interval t0, t1. So so this is contained in 0, is tf. Okay. So that outside of those two times, you are really not into the particle, the unperturbed particle doesn't see nothing about the support of your potential. This is sub dkl. And what this d now is, this d is exactly given by so this the norm omega 0 minus omega what was it? T minus the, and that is kind of large equal. You can do the similar thing as omega 0 t and the perturbed one, so the tilde corresponding to the thing with one element put off. So this is so this d is this. So it's clear now that if your q0, so your unperturbed thing of this harmonic oscillator, this position, so q of t, if that is if t is not in this interval, then your q0 of t is somewhere outside this interval, right? Somewhere here or somewhere there. And because this distance is bounded, then you can lift this exactly to there. And it holds also that the q of 0, so the q of 0, this is q0, so qt corresponds to the flow of the h of n, right? Maybe so q0 corresponds to this one, because this is kind of bounded in terms of the omega 0. So if this one doesn't see the potential because of this bounding, define this bubble just as this, then also omega 0 or omega itself will not be will not see in this sum. And the same also omega tilde, because this boundary is estimated in a similar way, because of our assumption of potential. But in those both cases, if you're outside this interval, your omega t, you have that if t is not an element of this interval which corresponds to the support of this v, it follows that omega t is omega 0 of t, is omega tilde of t. So this is very nice because it means that your both flows are just the same. Out this interval, they act just the same. In this interval, so if you are in this interval, then of course they are not the same anymore. But then you use the trick that if you give your beginning this assumption, if you put this energy large enough, meaning that this thing signal is very small, that the time it stays in this interval is kind of bounded by some epsilon. For this you use the Grunwald's inequality, so that you get kind of this inequality here. Don't go to the details, so you can bound omega t minus omega tilde of t, the norm of that. You can bound it in terms of some epsilon depending on the time on this conditioning. That means that in general, in total, for all the three times, so before, in, and out, you get exactly what you want. You get both flows are comparable, so they are getting the same, which is good for the next result. For this, you take an open cover of your omega lambda, of your part in your phase space. Take this open cover. I don't want to go that much into the details, but because you have this assumption here, that just means that the flow of this minus the flow that get kind of same. So if you don't take a function in your commutative resolved algebra, which by definition is uniformly continuous, and by uniform continuity, you see then that this here, because this element is nothing else than 2 points in phase space. Until you get close, you apply uniform continuity, it follows that the image gets close. So you get exactly that this gets close. Close disorder. And that is nice because we have another lemma proving that you can find a function that equals exactly this product of the flow of this g, so corresponding to this one here, on this u delta infinity. I don't want to go too much into the details, but the idea is to split this phase space all into a direct sum. for certain set T, and orthogonal complement, then you can show, you can prove that you can take an ideal in this CR omega lambda, and you can prove that the ideal is, idea now to prove that the ideal is stable, so this means the ideal is stable. And if you have this, then you can define a function f infinity is g tilde, kind of obtained by applying Coulson's lemma in some tricky way, times this. And if you can very easily apply this to observe. Maybe I should skip. You can. The idea is that having defined this and using the properties of this g tilde, which is indeed this g tilde can be shown to be in this ideal. You can manipulate this equation and see that the whole that f infinity is an ideal. Since the ideal is subset of the resultant algebra, you've proved that f infinity is in the resultant algebra, and that it equals this thing is a Klein matter of computation. But that's kind of the idea. So you have now find a function in your resultant algebra that equals the thing you want on this u delta infinity. So now these are the ingredients to prove really you get this stability. So you take G inside, you want to show that it's inside. The time evolution is inside. You do this by means of strong induction. That's why we needed this N here before. So you assume that the time evolution for this Hn minus Kl preserves it, each Kl in it. Okay, you have to show that for the Hn. For the Hn, that still preserves the resultant algebra. So the induction hypothesis is just this. You know it holds for this here. You can fix this function as before, and by uniform continuity, which we have seen before, you get this kind of inequality. The FKL restricted to those covers, so U delta KL minus this thing is small. This the trick, because having this this restriction, you now can construct the partition of unity. Because U delta KL, they cover the whole omega lambda, that allow you to construct a partition of unity subordinate to this cover, omega lambda. You can patch this function together in the final function, and there's a y, it should be a lambda. You can define a function in this commuted resultant algebra based on this FKL that approximates this time evolution unit in uniform normal. That's exactly what you want. So, you know this is small. Applying a couple of times triangular inequality, you can really find a function in the resultant algebra which approximates this, but the resultant algebra is not closed. It is in the C star algebra. So it means that this is approximated by a function like here, and so a norm. So you get that by definition if it's inside the resultant algebra itself. That's the idea. You apply a trick to get stability of this function itself. And if you now take the most general thing, take V was C01, so differentiable in tensor infinity, then it's just apply a density argument. You have this compactly supported, so it was not compactly supported. You can apply a density argument and extend this result very easily. And then you have basically proven that you have stability for the resultant algebra for this system. Starting with K symbol postulator, extending to the compact case, and then finally to the vanishing infinity. This does not, however, say you something about the limit. So now we go to extend this to the limit. So we basically now take a region, fixed region, you take again a levy, and you can estimate the Poisson bracket, and this is just an estimation. You can estimate in such a way, due to the assumptions on the potential this is bounded. And then you can, by theorem of Cardiff, you can rewrite this, the time evolution. The time evolution is given by the derivative, the vector field is the derivative of the flow, right? Integrating this, you get exactly this. So integrating the flow, you get exactly this. And now using the above estimate, you just can pull out this t, and you get this bracket, you have an estimate for this, manipulate a bit, and you can very easily see that both time evolutions, lambda 2 and lambda 1, the uniform norm, are bounded by this. So that basically means that you have Cauchy net, right? Because Cauchy net and lambda 1. So therefore, there's also a limit because we have a C star algebra, so that converges, and then you can prove that indeed this limit exists. This alpha gamma is that the limit in dynamics. Of course, once you prove that it indeed defines dynamics, so that it is preserved, there's no homomorphism, etc. But that is now not so easy, not so difficult anymore. This property here, this estimate, really allows you to have this limit, and the rest is then automatic homomorphism. Then you get a one subgroup of automorphisms on the result algebra, and you have this stability. So this is what you basically want. You have now proven, extended this stability, time stability to the whole omega. About the continuity is not clear yet. I didn't say nothing about this. So if you now consider this, the previous bounds imply that you have a kind of continuity on those compact sets. It's not so difficult to see because we have this T fixed. However, strong continuity is something you want in a C star algebra. That is something we don't have directly on the whole algebra because different directions, that's the result is the problem. If you consider results in different directions, then they are bounded from below by 1. They are not kind of, they don't go to smooth to 0. Different directions, orthogonal directions, for resolvents, they are bounded from below by a constant, by a non-zero constant. So then you don't get here, it's impossible to get strong continuity on the whole C algebra. To solve this, you introduce a subalgebra of your result algebra. This K, double K, C star of the K lambda plus identities, whereby K lambda is, I'll use the levies, so those levies we see before. The GPL, G composed of PL, then G is a C0 over lambda. This gives you a subalgebra with a roll, by the way. So K consists of those terms, right? They are the lambda direction and C0 plus constant, and the constant all the directions. The nice thing is that on this algebra you do have strong continuity. And the idea is to see this, that you really have strong continuity in this subalgebra, is that on K lambda itself, you see K lambda, you see this C0. Strong continuity on the C star algebra C0 is kind of automatic. If you have C0, then you have strong continuity. But for this, we really have to work so much. It's a known result. Who did those books, they write it. You can extend it to the whole of K again by some approximation what I showed you before here, by using Grunwald and some extension argument. But that can be done. So you get really strong continuity on your subalgebra, and more than that you can also not have. I mean, probably it's not true that you have strong continuity on all CI omega, but on this K you do have it, because K is related to compact operators, so in a non-commutative sense. Here meaning C0, and there you get that the results are just true, by no result, by no facts. So to move, the last thing to move a bit on with this idea, extended, the first thing we are still working on is to extend it to arbitrary mass and force constants. We now took it, in this proof I took everything constant, so the particles have the same mass, they rotate all with the same velocity. This in general it doesn't have to be the case. This will 100% this will work. There's just some technicalities we have to solve, and one technicality is this. This is those famous Lissajous figures. If they have different frequencies of masses, the rotations they combine into such strange Lissajous figures, and they are a bit more difficult to deal with than just circles, rotated circles. So you have to figure out a bit how how we apply the theory to such things, but that will work. A bit more complicated, just, but you still get continuity, strong continuity on this K, and time stability on CR. Another thing is, it's a bit more technical, as I said. Another thing is, we took those C0 potentials, right? So they are kind of vanishing on infinity, bounded vanishing on infinity. Maybe more interesting potential could be the Coulomb potential, in which case you see really a single kind of Coulomb potential which is interesting for physical reasons. So there is an open question. Does the dynamics still preserve the resultant algebra if you use a Coulomb potential rather than those C0 functions? And do we have strong continuity still in this K, in this sub-algebra? How does it work? Could be nice, because having defined this, you could also speak about interesting phase transitions, about KMS state, etc. If there's time stability, you are kind of in business, you have a C-star algebraic system, so you can start to speak about states and everything. And it would be nice to study it in this way, for these potentials. See phase transitions. So, last thing I want to tell you about is the classical K-mass condition, because there's something which is also related to this work. So, there is, we have seen several times, the standard K-mass condition in the sense of Bratelli-Robinson, right? That's just the thing we have seen several times these days. The idea is now, if you take now a limit into, if h bar goes to 0, in a very loosely speaking way. So, you can rewrite this into this form. That has been first observed by Galavotti and I think a Dutch guy Verboven. They observed to do this, and then what they did, take a semi-classical limit. So this commutator basically goes to the, you have to scale it, goes to a the commutator. So the a Poisson vector A and B. Now interpreted as functions, right? These are maybe operators, but loosely speaking, these are no functions. If you think about a quantization scheme by Reford or something, this should work. The similar thing you get here. This is kind of the derivative, right? You get this here. You get this. So, loosely speaking, one could think about taking such a limit and see what can happen. But that's exactly, let's take a potential without assuming too much things. You can then define, if you see this, this condition here, you can then define the K-mass condition just in this way. So the omega is state, for the commutative C-star algebra, and it should be a limiting case, it should be commutative. Applied on this Poisson bracket should be given by the state itself, G times XHF. So XHF is nothing else than the vector field, Hamiltonian vector field, for some suitable F, probably localized. I don't want to go into these details, but this is the way you derive the classical chemistry. This, of course, does not make sense if your omega you have no Poisson structure. So in a discrete case, so if you take the very first example I showed you, that you have discrete systems with a finite set, then you cannot have such a symplectic structure. So it makes you sense to speak about the classical K-mass condition. If you have, in our case, there's R2n as R2 small n as single side space, you have a symplectic structure, you have a Poisson structure. And then you have this, you can speak about this condition. It makes sense to speak about it. And it makes also sense to compare this condition with the DLR equations. So the famous DLR equation by Dubroschian, Jan van der Velde. Is it an equivalent? So does the state satisfy this classical K-mass condition if it satisfies the DLR conditions, which is kind of important to measure equilibrium in classical statistical mechanics. And we know that K-mass states from Bratelli-Robinson are quantum, and even DLR can be seen as an equivalent to the K-mass condition from Bratelli-Robinson. You can embed this DLR formalism by using a diagonal argument. You can see this as equivalent in some. You can embed those classical interactions with a diagonal argument in a C-star algebra. This is really equivalent. But is it equivalent to this condition? That is not known yet in this framework. It is. This is just a question. To do this DLR condition, does this equivalent to the classical K-mass condition? That would be nice. If you have that, you have an equivalent notion of thermodynamic equilibrium. You can just switch to both. This is solved by me and Drago in a paper which is just accepted also. It's good. In case the single side part of the space is symplectic connecting compact. So in case of those spheres, think about those spheres. You spin system on those spheres. It is symplectic. You can prove that this is really equivalent. So this is a nice result in case of lattice systems. It is known. This result is known In case of so R6, so R3 times R3, in which you then consider like infinite particles. But that is not a lattice system because your configuration, so your phase space is just fixed. This just goes about, these results, it goes about increasing your number of lattices, so lattice systems. And in case of the unbounded sinusoid space, in case we have studied today, it is no problem. We don't know if there's still, we still have this equivalence between this interplay between classical KMS and the KMS condition of the DLR equations from which are better known probably. That is what I want to close this talk with those remarks. It is kind of research progress to formulate the equilibrium by means of these KMS states, and then maybe study phase transitions by proving that there are multiple states satisfying this condition. That is, then would be a phase transition. For this is a mistake, I didn't write in beta, but of course it should be everything should depend on your inverse temperature. But this is what I want to close with this. So thank you very much for your
Great, thank you, Christiaan. Are there any questions?
Can you point out where exactly is the defect of the formulation of the classical KMS? I guess it's the next.
Yeah, probably, but the problem is I forgot to put it right there. It should be there.
Is there a plus one bracket on the right hand side?
Yeah, yeah.
Or is it
because
also
it's
this one?
It's this one. This one.
Oh,
So that's the so that condition is
G is
yeah.
simply pointwise multiplication.
Yeah, yeah. This is you should see A0 as a classical commutative algebra. So G times this function XHF is again a function of just pointwise multiplication. Yeah, because that's the property of this algebra. That's but the idea to generalize this to such systems that to see if you really have this equivalence also for unbounded phase space. For compact space, it's relatively easy to do this because you don't have those limiting procedures. It's kind of really easy. Your infinite product is compact by Tikhonov, so this will be more easy here. That should work probably a bit more for case of R2n. Yeah.
You can just go a little bit more, go further in the presentation, please.
So back here?
No, go and then forward, yes. Yeah, yes, you say that you are interested in do some kind of for the labs, but about the spin system you're saying, right? Like R or something.
Yeah. So the situation I sketched in the whole presentation was R2 small n. And there you have a symplectic structure, you can define a bracket. So this Poisson bracket I sketched in the really beginning of the presentation, you can still require, you can ask if this
yes,
so
I mean,
make this working and prove that it's equivalent to DLR.
But what happens is that, there is a group in Bielefeld, right? Kondrayev and these people.
Bielefeld?
Yes, there is because actually there are few people doing unbounded speed system because, you have a lot of obstructions, and one of them, when you start to do this, is that your partition function is that you can explode if you don't choose really the good, right? Yeah. So there is some proposals. Right?
Yeah, for KMS functionals rather than states, so we don't do the normalize.
Yes, I don't know, but what I'm saying that, let's say, even what people did as Kondrayev and also Abel, people like that, they try to do something, but in general they arrive at some kind of they call temperated configuration space. They took off a part of the. I don't know if you have let's say a direction when I can deal with the complete state configuration space.
Yeah, I see your point. In this case, in this lab, it should work because omega. So in the previous part, the omega was just those space of finite sequences, right? That and you have a Poisson bracket on top. Those in the beginning and.
So I mean, you can deal with let's say unbounded spin power to CD, for example.
Yeah.
Is possible.
Yeah, so in this setting, we want to go back to this here, this setting, this is the omega. Your Poisson bracket is kind of this. And then the question is, you have to define stage. You have to think about technicalities because it should, local observers should think about it, but that probably should also work because you have this inductive limit. Now, you have this inductive limit structure, so you can really localize your observables in finite paths. Because you have this in. So I think in this case it should work. Just it's complicated to calculate an explicit example. So take, for example, instead of the potential, see, so take a Coulomb potential, which is maybe more interesting. And then see if it really, if you get really in phase, if you really prove the existence of phase transition in such framework. That could be, yeah, that's the thing I was thinking about. That is, but then I didn't investigate that yet. Yeah. That should basically work, but there's two it goes wrong. But this R2N that has the structure you want, basically. So I think it's, yeah.
Great, thank you. I think it's coffee time. Is there anyone that has like a very quick question with a very quick answer? If not, I think we should. You promise a quick question and quick answer, then you can go.
Just make sure with this classical chemistry state, you're still asking that the boundary condition is free.
Good question. That depends basically on the model you consider. If your Hamiltonian you take, because it depends on your vector field, right? Your Hamiltonian vector field, so x8 of f depends on the Hamiltonian. We did this. It is not necessary. In our paper with Nicolas, that was not necessary because it didn't turn out that you have these conditional probabilities, and the DLR equation is just made for having this boundary. So there's conditional. So you fix a lambda in your big space. You take the complement of it, and you take the configurations inside omega. So omega lambda complement, and then DLR equation I just invented for this reason to model this boundary and those conditions. So that kind of worked. In this case, I'm not sure. I'm not sure. So thank you.
Great. Let's thank Christiaan once again. And I think there's a coffee break for